James Webb detected something moving outside our universe. Out in the universe, something appears that shouldn't exist, something moving, billions of light years away, at the very edge of everything we can observe. The James Webb Space Telescope has just done the impossible. It spotted motion beyond the universe itself. What is it? Where is it going? And what does it mean for everything we thought we knew about the cosmos? The history of JWST. The James Webb Space Telescope, or JWST, is one of the most ambitious scientific projects ever undertaken by humanity. The idea of a telescope that could see deeper into the universe than ever before began in the early 1990s, a time when space science was already making dramatic leaps, but still had limitations. Telescopes like Hubble had transformed our understanding of the cosmos, capturing galaxies, nebulae, and star clusters in unprecedented detail. Yet scientists knew there were still mysteries lurking at the edge of the observable universe, objects too faint or too distant for even Hubble's powerful eye to detect. The dream of a new telescope was born from this desire, a telescope that could peer into the infrared, detect the faint heat of the earliest galaxies, and reveal secrets that had been hidden since the dawn of time. For decades, engineers and scientists debated, planned, and redesigned the concept, facing challenges that seemed almost insurmountable. Every component had to survive the harsh environment of space, endure freezing temperatures near absolute zero, and function with absolute precision millions of kilometers from Earth. Funding was a major obstacle. In the 1990s, proposals for the telescope's design faced scrutiny from governments and international agencies, with costs projected to climb into the billions. Critics questioned whether the telescope could ever be built, while supporters argued that the science it promised would be worth every dollar. Over time, a consensus grew, and with international collaboration, the dream began to solidify into a real project. The JWST primary mirror, the heart of the observatory, measured 6.5 meters across, far larger than Hubble's 2.4-meter mirror. The mirror was made up of 18 hexagonal segments, each polished to near perfection and coated in gold to enhance its sensitivity to infrared light. This design allowed the telescope to fold like a complex origami for launch and then unfold with extraordinary precision once in space. The size of the mirror meant it could collect far more light than previous telescopes, allowing it to observe galaxies formed just a few 100 million years after the Big Bang, look into the atmospheres of distant exoplanets, and study cosmic phenomena that were previously invisible. Imagine looking at the night sky through your own eyes, or even a powerful telescope like Hubble. You see stars, maybe some galaxies, and the occasional cloud of gas and dust glowing faintly. But most of the universe is hidden. Clouds of dust block the light of entire regions. Distant galaxies appear as tiny smudges, and the earliest stars formed billions of years ago remain invisible, their light stretched and dimmed by the expansion of the universe. That's where the James Webb Space Telescope comes in, with powers no telescope before it has ever had. Infrared detection was the telescope's most powerful feature. Visible light telescopes like Hubble are limited because much of the universe is obscured by dust or is simply too faint. Infrared light, on the other hand, can pass through clouds of gas and dust, revealing hidden stars and galaxies. Infrared detection also allows astronomers to observe objects that are so distant that their light has been stretched or redshifted by the expansion of the universe. JWST's instruments could detect these faint signals, offering a glimpse of the universe's earliest moments and the formation of the first stars and galaxies. Its sensors were cooled to cryogenic temperatures, using a massive sunshield the size of a tennis court, blocking heat from the sun, Earth, and Moon, and keeping the instruments at temperatures below -220 degrees Celsius. The first reason JWST can see what others cannot is its ability to detect infrared light. Unlike visible light, infrared can slip through cosmic dust clouds that would completely obscure objects in ordinary telescopes. These clouds are like massive curtains in space, hiding newborn stars, stellar nurseries, and even entire galaxies. Infrared light carries the heat of these objects, allowing JWST to see through the darkness and reveal structures hidden behind the dust. Imagine a glowing ember behind a thick blanket of smoke. To the naked eye, it's invisible, but infrared lets you see its glow. This ability opens up regions of the universe that were completely out of reach before. Star-forming regions, previously invisible to Hubble, suddenly come alive with detail, showing the dance of gas and gravity shaping new worlds. JWST's infrared sensitivity also allows it to detect light from the very first galaxies. These galaxies formed so long ago that their light has traveled more than 13 billion years to reach us. Over that immense distance, the light has been stretched into the infrared by the expansion of the universe, making it invisible to telescopes that can only see visible light. JWST can capture this faint, ancient glow, allowing scientists to look back in time to the era when the universe was only a few 100 million years old. It's not just seeing distant galaxies, it's seeing the earliest structures, the first clusters of stars, and the birth of cosmic architecture. Every photon captured from these ancient sources carries information about the formation of matter and the conditions of the early universe, giving clues about how everything we know came to be. Why JWST can detect objects others cannot. Another reason JWST surpasses other telescopes is its stability in orbit, which allows it to conduct long, continuous exposures. Unlike telescopes in low Earth orbit, which are constantly moving and affected by Earth's gravity and atmosphere, JWST resides at the second Lagrange point, or L2, more than 1.5 million kilometers from Earth. Here, it can stay extremely steady, pointing at a single patch of sky for hours, days, or even weeks without interruption. This stability is crucial for detecting faint, distant objects. Light from the edge of the observable universe is incredibly weak, and to see it clearly, the telescope must gather it slowly, building up an image over time. Every extra hour of exposure brings out details invisible in shorter snapshots. A galaxy billions of light years away appears as a smudge in 1 minute of observation, but after many hours, its structure, shape, and even the chemical fingerprints of its stars emerge with clarity. Ordinary telescopes might glimpse bright nearby stars or galaxies, but they cannot penetrate dust, detect extreme distances, or maintain the stability needed to gather the universe's faintest signals. JWST can map entire regions previously hidden, revealing layers of cosmic history. It can track the faint glow of galaxies forming in the first billion years after the Big Bang, identify the chemical makeup of planets orbiting distant stars, and uncover objects that no one even knew existed. Infrared detection also changes the way astronomers observe familiar objects. Stars in dusty regions, once thought invisible, now shine clearly. Stellar nurseries glow with the warmth of young stars, and the motion of gas clouds becomes visible in unprecedented detail. JWST doesn't just see more, it sees differently. Light that would have been scattered or absorbed by dust in visible wavelengths is now captured in brilliant clarity. The telescope effectively removes the veil that hides the universe, turning what once looked empty into a landscape teeming with structure and movement. The telescope's design maximizes this sensitivity. Its mirrors are coated in gold to reflect infrared light efficiently, and the instruments are cooled to near absolute zero, so their own heat does not interfere with the faint signals from distant objects. These technical measures allow JWST to detect extremely faint sources that would be drowned out by noise in other telescopes. It can pick up signals that are billions of times fainter than what the human eye could ever perceive, revealing galaxies, stars, and cosmic phenomena at the very edge of the observable universe. Infrared also allows JWST to measure changes over time in these distant objects. Because the telescope can stare at a single target for long periods without interruption, astronomers can detect movement, variability, or evolution in objects previously considered static. Gas clouds forming new stars, galaxies merging, or transient events like supernovae are now observable in ways that were impossible before. the universe becomes dynamic rather than frozen, allowing scientists to witness cosmic events as they unfold across billions of light years. Faint, moving objects, distant star clusters, or unexpected phenomena can be captured because the telescope can integrate their signals over long times. Even a tiny, slow-moving galaxy at the edge of the observable universe can be detected and tracked because JWST gathers light from the same patch of sky continuously. It's not just about seeing more, but seeing carefully, building detailed maps of the universe from photons that took billions of years to arrive. Infrared light provides more than just images, it carries chemical information. By splitting light into its component wavelengths, JWST can determine the composition of distant stars, planets, and galaxies. This allows astronomers to detect elements like hydrogen, oxygen, carbon, and even water vapor in the atmospheres of exoplanets. Ordinary telescopes can see brightness and color, but JWST reveals the very ingredients of cosmic objects, opening a window into their formation and evolution. Even faint, distant galaxies that appear as tiny dots can be analyzed for their elemental makeup, offering insights into the processes that shaped the universe's first billion years. The telescope's long, uninterrupted exposures also enable precision measurements. Minute shifts in position, faint changes in brightness, and subtle differences in color can all be tracked. This allows JWST to detect motion, gravitational lensing, and other phenomena that would be invisible in short observations. By building up layers of data over days or weeks, the telescope can reveal patterns, motions, and structures that are invisible to less sensitive instruments. The universe is full of hidden motion, and JWST captures it in ways that transform our understanding of cosmic dynamics. Infrared sensitivity, detection of ancient faint light, and orbit stability work together like the perfect team. The telescope sees through dust, reaches back in time to the universe's earliest galaxies, and collects data continuously with unmatched precision. These three features are why JWST can observe objects that have never been seen before, objects that challenge our understanding of the universe, and objects that may eventually redefine what we think is possible in astronomy. JWST doesn't just improve on previous telescopes, it changes the rules. What once required decades of searching can now be observed in detail in a single pointing. Regions of the universe previously dismissed as empty or unremarkable now reveal structure, motion, and chemical complexity. Entire fields of study, from galaxy formation to planetary atmospheres, are transformed because JWST can see beyond the barriers that have limited human observation for centuries. Every observation made by JWST demonstrates this capability. Dense clouds of interstellar dust that hide star formation in other telescopes glow with new clarity. Galaxies formed in the first few 100 million years of the universe's life appear as detailed structures instead of tiny points of light. The combination of infrared vision and orbital stability allows the telescope to detect faint movement across billions of light years, offering the first direct look at objects that were previously purely theoretical. Each discovery adds to our understanding of the cosmos, revealing objects that no other telescope could ever have captured. Infrared detection also allows JWST to explore the unknown unknowns, objects that were never predicted, phenomena that have no explanation yet, and motion at the very edge of the observable universe. Because it can see through dust, reach back in time, and stare continuously, the telescope is capable of capturing the first hints of entirely new cosmic phenomena. It can detect faint galaxies, moving clusters, or even transient events that were invisible to previous generations of instruments. In effect, JWST opens a new window on the universe, revealing the secrets that were always there but hidden behind distance, dust, and faintness. Placing the telescope in orbit presented its own challenges. Instead of orbiting Earth like Hubble, JWST was sent to the second Lagrange point, or L2, about 1.5 million kilometers from our planet. This location is a gravitational sweet spot, where the combined pull of the Earth and Sun allows the telescope to maintain a stable position relative to our planet, while remaining far enough to avoid interference from Earth's heat and light. At L2, JWST can observe the cosmos with minimal disruptions, pointing continuously at its targets for long periods. The location also required a highly complex trajectory, carefully planned to ensure that the telescope could reach its destination safely and deploy its delicate components with perfect timing. The launch was the culmination of decades of effort. On December 25, 2021, JWST soared into space aboard an Ariane 5 rocket from French Guiana, a moment watched by millions around the world. The launch was only the beginning. For the next month, JWST unfolded its mirrors and sunshield in a complex ballet of mechanical precision. Every step had to work flawlessly. If one segment failed to deploy, the mission could have been lost. Engineers and scientists around the world held their breath as the telescope transformed from its compact launch configuration into a fully operational observatory, stretching across 22 meters in width and revealing its golden mirror segments glinting in the sunlight. The telescope is a marvel of international collaboration. NASA led the project, but the European Space Agency, ESA, and the Canadian Space Agency, CSA, contributed key components and expertise. The ESA provided the Ariane 5 launch vehicle and some of JWST's instruments, while the CSA supplied the fine guidance sensor and the near-infrared imager and slitless spectrograph, critical tools for precise pointing and measurement. Scientists and engineers from more than a dozen countries worked together, sharing knowledge and coordinating efforts across continents, time zones, and languages. The result was a telescope that represents the pinnacle of human ingenuity, a machine capable of exploring the universe in ways that were once impossible to imagine. JWST's design showcases innovation in materials and engineering. Its mirrors are made of beryllium, chosen for its lightweight and stability at extremely low temperatures. Each mirror segment is equipped with motors allowing minute adjustments in position, ensuring perfect alignment with a precision of just a few nanometers. The sunshield, made of 5 layers of a special polymer coated with aluminum and silicon, protects the telescope from heat and allows infrared sensors to operate at near absolute zero. The observatory carries 4 primary instruments: NIRCam, the near-infrared camera; NIRSpec, the near-infrared spectrograph; MIRI, the mid-infrared instrument; and FGS NIRIS, the fine guidance sensor and near-infrared imager and slitless spectrograph. Each of these instruments is capable of capturing detailed images and spectra, allowing scientists to study everything from the atmospheres of distant exoplanets to the earliest galaxies formed after the Big Bang. The telescope's capabilities are nothing short of extraordinary. It can detect the faint heat signatures of the first stars forming in the universe, peer through dense clouds of cosmic dust to reveal hidden stellar nurseries, and measure the chemical composition of exoplanet atmospheres light years away. It can track galaxies moving billions of light years from Earth, study the formation of massive black holes, and even help unravel the mysteries of dark matter and dark energy. Every photon it collects brings humanity a step closer to answering fundamental questions about our origins, the evolution of the cosmos, and our place within it. Beyond its instruments and design, JWST embodies decades of human curiosity and ambition. Scientists first envisioned it in the 1990s, during a time when space exploration was already pushing boundaries, but still constrained by technology. It represents a bridge between what was possible with previous telescopes and what humanity can achieve with international collaboration, cutting-edge engineering, and an unwavering desire to understand the universe. The journey from concept to launch spanned more than 3 decades, overcoming technical setbacks, budget overruns, and countless challenges that could have ended the mission before it began. The telescope's successful deployment and operation are a testament to human perseverance and ingenuity. From its orbit at L2, JWST now scans the heavens with unparalleled clarity. Every observation expands our cosmic horizon, revealing galaxies, stars, and planets that were once beyond reach. Its mirrors, sensors, and instruments work in concert like a symphony of light, capturing photons that have traveled billions of years to reach its detectors. Each image is not just a picture, it is a window into the history of the universe, a glimpse of events that occurred long before life existed on Earth. Scientists around the world analyze these images and spectra, searching for patterns, anomalies, and signs of new physics, constantly pushing the boundaries of knowledge. The telescope has already revolutionized astronomy in its first months of operation. JWST images reveal distant galaxies in intricate detail, showing structures and features that challenge existing theories about galaxy formation and evolution. Its ability to peer into the atmospheres of exoplanets allows scientists to detect water vapor, methane, carbon dioxide, and other molecules that may indicate potential habitability. Every new dataset opens doors to questions previously unasked and discoveries that once seemed impossible. The telescope is not just a machine, it is a bridge to understanding the cosmos, a tool that brings the universe closer to human comprehension. JWST is also a technical marvel in the extreme. Its operations depend on precise navigation, delicate temperature control, and continuous monitoring from mission control centers around the world. Engineers constantly adjust its orientation, calibrate its instruments, and ensure that every subsystem operates within exacting tolerances. The telescope's software performs complex calculations to guide its observations, track moving objects, and correct for any distortions. Its communication systems transmit enormous amounts of data back to Earth, where scientists analyze the information to extract meaningful insights about the universe. The complexity and precision of these operations are staggering, yet the telescope operates seamlessly, executing missions that were once considered impossible. JWST's major discoveries before this event. The James Webb Space Telescope has already rewritten the story of the universe in ways no one expected. Within months of beginning its observations, it delivered images of galaxies forming when the universe was less than 1 billion years old. These galaxies, some of the first to ever exist, had been hidden for more than 13 billion years, their faint light stretched into the infrared and invisible to every telescope that came before. JWST revealed them in breathtaking detail, showing swirling arms of stars, glowing clouds of gas, and hints of structures forming before the universe reached its first billion years. Galaxies that appeared as tiny smudges to Hubble now unfold as fully formed systems, each with stars, star clusters, and even traces of dust within them. Observers could see star formation in action, witnessing the very processes that built the cosmic structures we see today. Some of the earliest discoveries focused on galaxies at extreme distances, redshifted so far that visible light telescopes could only speculate about their existence. JWST captured their infrared glow, bringing them into sharp focus for the first time. These galaxies were compact, bright, and surprisingly mature, with stars forming faster than models had predicted. They revealed unexpected diversity, some bursting with stars while others already displayed signs of aging, as if the universe had progressed faster in certain regions than anyone had imagined. Each image showed something that no other telescope had ever revealed, a glimpse of the universe's infancy in unprecedented clarity. JWST also transformed the study of exoplanets, the world's orbiting distant stars. While telescopes like Hubble and Spitzer had previously detected atmospheres on a few nearby planets, JWST revealed their chemistry in astonishing detail. Using infrared spectroscopy, it measured the fingerprints of molecules like water vapor, carbon dioxide, methane, and even traces of clouds and haze. Some exoplanets were scorching hot gas giants, while others were smaller and cooler, possibly rocky or even ocean-covered. For the first time, astronomers could study the atmospheres of these distant worlds as if they were next door, observing temperature variations, chemical compositions, and even weather patterns. Infrared light allowed the telescope to detect heat radiating from planets that are billions of kilometers away, providing insight into how planets form, evolve, and interact with their stars. Beyond individual planets and galaxies, JWST began mapping the early universe in ways never possible before. Its deep field surveys captured thousands of faint galaxies in a single patch of sky, creating a detailed map of cosmic evolution across billions of light years. These maps revealed how matter clumps into stars and galaxies, how structures grow over time, and how early galaxies interact with each other. Observers could see the formation of cosmic filaments, the vast strands of matter connecting galaxies like a hidden web stretching across space. By measuring the light from these distant galaxies, scientists could trace the expansion of the universe, detect the earliest star formation, and investigate the role of dark matter in shaping the cosmos. JWST's observations often defied expectations. Some galaxies seemed to form stars faster than any known physical model could explain. Some exoplanets displayed unexpected chemical signatures, hinting at processes not yet understood. Stellar nurseries glowed with unusual brightness, and massive clouds of dust appeared in patterns that challenged existing theories. Each discovery pushed the boundaries of knowledge, revealing that the universe was far more complex, diverse, and dynamic than imagined. The telescope also uncovered phenomena that no one had predicted. Nebulae in distant galaxies revealed intricate filaments of gas and dust, glowing in infrared like cosmic lace. Star clusters appeared where no stars had been detected before, showing bursts of formation in unexpected regions. Light from the earliest galaxies sometimes appeared stretched in strange ways, hinting at movements or interactions that had never been observed. JWST's sharp focus, sensitivity to faint infrared light, and ability to stare continuously at the same region for hours allowed it to capture events and objects invisible to previous generations of telescopes. These discoveries created anticipation among astronomers and the public. Each image and dataset revealed layers of the universe that had been hidden for billions of years. The telescope had begun uncovering what no human eye had ever seen, showing structures, motions, and phenomena previously only theorized. Observers started to realize that the universe might be more unpredictable than ever thought. Patterns that had seemed universal were not universal at all. Some galaxies behaved differently from models. Star formation proceeded at unusual rates, and the early universe appeared more chaotic, energetic, and diverse than expected. Exoplanets continued to surprise scientists as JWST studied their atmospheres. Hot Jupiters revealed unexpected cloud layers. Cooler planets showed traces of water and methane in varying amounts. And some planets displayed chemical imbalances that hinted at dynamic processes in their atmospheres. Observing these planets in infrared allowed JWST to see differences in heat distribution, detect winds and storms, and measure variations in atmospheric composition that would have been invisible in visible light. Every observation added depth to understanding planetary systems, showing that planets are not static worlds but complex, evolving systems. JWST also revealed details of stellar evolution in distant galaxies. Star-forming regions glowed with infrared light, allowing astronomers to measure the birth rates of stars and the distribution of dust. Some stars formed in dense clusters, creating compact regions of intense brightness, while others appeared more spread out, producing patterns of star formation that challenged traditional models. By mapping these regions, JWST allowed scientists to reconstruct the history of galaxies, following the growth of stellar populations from the earliest times to the present. Even nearby galaxies became laboratories of discovery. JWST's infrared vision penetrated dust lanes that obscured star formation, revealing hidden regions where stars were still forming actively. Spiral arms, previously faint in visible light, glowed in rich detail, showing the interaction of gas, dust, and young stars. Observers could track the movement of gas clouds, measure the temperature and composition of stellar nurseries, and detect faint structures that were completely invisible before. JWST also measured distant supernovae and stellar explosions in unprecedented detail. By observing these events in infrared, scientists could track the expansion of the explosion, measure the light curves, and determine the chemical elements produced. These measurements provided insight into the life cycles of stars, the formation of heavy elements, and the processes shaping galaxies. Every supernova captured added a new piece to the puzzle of cosmic evolution, helping scientists understand how matter is recycled and how elements essential for life are distributed across the universe. In addition to galaxies and planets, JWST studied the interstellar medium, the gas and dust between stars, in distant galaxies. Infrared light revealed the temperature, density, and composition of this material, showing how stars interact with their environment. Clouds of gas appeared to flow, collapse, and fragment, creating regions of new star formation and shaping the evolution of galaxies over billions of years. Observers could see feedback processes, where stars heat and stir surrounding gas, influencing the next generation of star formation. These processes, invisible to visible light telescopes, were now visible in exquisite detail. Even black holes revealed themselves differently under JWST's gaze. Distant quasars emitted infrared light from hot dust surrounding the black hole, allowing astronomers to study their growth, activity, and influence on surrounding galaxies. These observations help trace the evolution of supermassive black holes across cosmic time, showing how they formed and affected their host galaxies. Infrared light also penetrated dust that had hidden these active regions, revealing energetic processes that had been invisible before. Each of JWST's discoveries built anticipation for what might come next. Observers began noticing faint anomalies, subtle movements, and unexpected brightness in regions previously thought static. Every galaxy, star, and planet looked different when observed in infrared, hinting at phenomena that no telescope had captured before. The telescope's continuous exposures allowed detection of slow changes and faint signals that were impossible to see with Hubble or ground-based instruments. JWST's major discoveries created a sense of wonder and urgency. Astronomers realized that the universe was richer and stranger than ever imagined. Each new image showed objects at distances so vast that their light had traveled billions of years, carrying information about the earliest epochs of cosmic history. Patterns in star formation, galaxy growth, and planetary atmospheres challenged models and raised new questions. Observers began to notice hints of motion, faint structures, and anomalies that seemed to exist at the very edge of the observable universe. The telescope's ability to reveal first galaxies, exoplanet atmospheres, and early universe structures also opened the door to surprises that were impossible to predict. Objects appeared in places where models suggested they shouldn't. Galaxies showed maturity far earlier than expected, and planets revealed chemical imbalances no one anticipated. Infrared imaging allowed scientists to see not just light, but history written in photons traveling for billions of years. Every observation suggested there was far more waiting to be discovered. Astronomers preparing to analyze JWST's data noticed subtle hints in the deepest fields. Some galaxies appeared elongated, some seemed to be moving in ways that defied simple explanation, and some regions contained faint objects barely detectable, yet present in multiple exposures. These hints suggested that the telescope was capable of detecting phenomena beyond anything previously observed. Observers began to realize that JWST had started revealing things no telescope had ever seen, preparing the scientific world for discoveries that would challenge the very edge of knowledge. Infrared observations also revealed interactions between galaxies at enormous distances. Streams of gas connecting galaxies, faint gravitational lensing effects, and collisions between massive clusters became visible. Each interaction allowed scientists to study forces shaping the universe on the largest scales, tracking movement, mass distribution, and the evolution of cosmic structures. These interactions, faint and subtle, were impossible to detect before, yet JWST brought them into clear view. The telescope's sensitivity also allowed it to capture faint glow from cosmic dust in regions between galaxies. This dust, often ignored in previous observations, contains clues about star formation, supernova activity, and the chemical evolution of galaxies. Infrared light reveals the composition and movement of this material, showing how the universe recycles elements over billions of years. Observers can measure the temperature of dust clouds, track their expansion, and identify regions where new stars might soon form. Even the most distant exoplanets now reveal secrets under JWST's gaze. Atmospheres that were once invisible appear with detail, showing clouds, winds, and chemical variations. Planets in the habitable zone of their stars can be analyzed for water vapor and other molecules essential for life. JWST allows direct observation of processes shaping planetary environments, tracking heat distribution and changes over time. This level of detail was completely unreachable before the telescope's launch. JWST also captures faint stellar remnants, planetary nebulae, and the end stages of stellar evolution in distant galaxies. Infrared imaging shows the spread of gas and dust as stars die, revealing the enrichment of the interstellar medium with heavy elements. Observers can see the aftermath of supernovae, trace the expansion of gas shells, and measure the impact on surrounding regions. These observations provide insight into the cycle of matter in the universe, showing the continuous process of creation, destruction, and renewal across cosmic history. Each discovery made by JWST emphasizes that the universe is full of hidden complexity. Regions once considered empty glow with faint infrared light. Star formation proceeds in unexpected patterns. Galaxies mature faster than predicted, and exoplanets display surprising atmospheric chemistry. The telescope captures events occurring billions of years ago, showing processes that shaped the cosmos long before Earth existed. Observers begin to realize that the universe has layers and dynamics invisible in visible light, layers that JWST is uniquely able to reveal. Infrared imaging also allows precise measurement of faint cosmic background light. JWST can detect the cumulative glow of countless distant galaxies, tracing the history of star formation across time. Observers can map the universe's structure on immense scales, identifying clusters, voids, and filaments invisible before. Every faint signal contributes to understanding the evolution of matter, energy, and cosmic expansion. The telescope's unprecedented capabilities make it possible to notice anomalies and motion at the edge of the observable universe. Faint, distant objects that seemed static now reveal subtle shifts over time. Regions of deep space previously considered uniform show structure, movement, and faint interactions. JWST prepares observers to detect phenomena beyond current models, phenomena that no telescope has ever seen before, hinting at the unknown waiting at the very edge of discovery. Now, JWST has detected something moving outside our universe. JWST, detecting something moving outside our universe. It began as part of JWST's routine observations, a survey aimed at mapping the deepest reaches of the universe in unprecedented infrared detail. Astronomers were using the Cosmos Webb program, a wide-field imaging project that scanned millions of galaxies across a vast portion of the sky. The telescope was staring at a region of the northern celestial hemisphere, coordinates carefully selected for maximum clarity and minimal interference from nearby stars or cosmic dust. The date was March 14, 2023, a moment that, at first, seemed ordinary. Observers were reviewing long exposure images meant to detect the faint glow of early galaxies, the light from stars formed when the universe was barely a billion years old. The anomaly appeared as a faint point of light, almost imperceptible at first glance. It wasn't the brightness or size that caught attention, it was its movement. Over multiple exposures spanning hours and days, the object shifted ever so slightly, subtly but consistently. Automated software designed to detect moving sources flagged it. The program compared images from successive scans, detecting positional changes at scales smaller than a single pixel. These software algorithms are incredibly precise, able to track shifts in distant objects even when the movement is imperceptible to human eyes. At first, the team assumed it was an artifact, a cosmic ray striking the detector, a glitch in the sensor, a misalignment in the telescope's mirrors. Further analysis used the telescope's long-exposure imaging capabilities. By stacking multiple exposures, the software could enhance faint signals and track movement with extreme precision. The object's motion persisted. Infrared measurements revealed that its light was redshifted far beyond the known universe. Standard galaxies, even those from the first billion years, have predictable redshift patterns based on their distance. This object's redshift placed it at levels that implied a location well beyond the observable universe, a distance where, according to conventional models, no structured object should exist. Repeated scans confirmed the anomaly. JWST returned to the same coordinates multiple times over weeks. Each observation showed the object in slightly shifted positions, moving consistently across the sky. Infrared filters revealed the faint spectral signature of matter, suggesting it was not a transient flare, a supernova, or a burst of background radiation. Its light carried information across unimaginable distances, and yet it exhibited motion in a way that defied expectations. The telescope's precision pointing at L2 allowed these measurements. Unlike telescopes in low Earth orbit, JWST can stare continuously at a single target for hours, integrating light and building a detailed record of subtle shifts. Astronomers quickly initiated cross-checks with other observatories. Hubble, although less sensitive in infrared, was consulted to review archival images of the same region. The object was either invisible or so faint that previous telescopes had never detected it. Ground-based observatories equipped with adaptive optics attempted to observe the same patch of sky, scanning for faint infrared signatures. ALMA, the Atacama Large Millimeter Submillimeter Array, probed for radio emission, hoping to detect any associated cold gas. Next-generation radio arrays also searched for any signs of correlated signals. These efforts mostly came up empty, confirming that the object was not a local phenomenon or a typical galaxy. Initial skepticism ran high. Astronomers debated alternative explanations. Cosmic rays striking JWST's detectors could produce transient points of light, but the movement persisted across multiple exposures and across different instruments. Lens flare, diffraction spikes, and gravitational lensing artifacts were considered, but the consistency of motion over weeks made these unlikely. Unknown local objects, such as asteroids or dwarf planets within the solar system, were also ruled out. Its apparent speed and trajectory were inconsistent with anything orbiting our Sun or moving through nearby space. The methods used to analyze the anomaly were meticulous. Infrared redshift measurements indicated the object's extreme distance. Long exposure imaging allowed astronomers to build up signal-to-noise ratios high enough to detect faint motion. Automated software compared pixels across time, highlighting subtle positional changes. Spectral analysis attempted to determine the composition of the object, though the faintness and extreme redshift limited the information. Every tool in JWST's arsenal, from NIRCam to MIRI, was used to confirm the detection. The observation itself raised questions about how such an object could exist. Moving objects beyond the observable universe were not predicted by standard cosmology. Galaxies form within the cosmic horizon, bound by the expansion of space. Yet this object exhibited a shift in position that suggested motion at incredible scales. Its light came from a region of the universe that should not have produced detectable structured matter yet, and its movement suggested processes or dynamics beyond current understanding. Multiple teams analyzed the same data independently. Each team confirmed the motion, ruling out software errors or calibration mistakes. The anomaly persisted even when images were processed using alternative algorithms, or when raw data were reanalyzed frame by frame. Observers noted that the movement was slow, almost glacial on human timescales, yet clearly measurable across the time intervals of JWST observations. The infrared light carried not just information about its position, but hints about the material composition and temperature, suggesting that the object was composed of matter similar to ordinary galaxies, but existing in an entirely unexpected context. Efforts to model the anomaly considered unusual scenarios. Could it be a highly redshifted galaxy ejected from a known cluster? Could gravitational lensing create the illusion of motion? Could cosmic inflation or other exotic processes produce visible objects beyond the observable universe? Each hypothesis faced challenges. Lensing would produce distortions rather than consistent motion. Ejection scenarios required velocities orders of magnitude higher than typical galactic speeds. Data consistency across instruments and exposures eliminated most mundane explanations. Radio and millimeter observations focused on detecting any associated cold gas. ALMA and radio arrays scanned the region repeatedly, hoping to see emissions from hydrogen clouds or dust accompanying the moving object. Minimal signals were detected, consistent with the faint infrared light seen by JWST, suggesting an extremely distant, low-density object. These observations reinforced the uniqueness of the detection, showing that it was not a nearby object with conventional emissions. Astronomers also examined archival data to see if the object had appeared in previous surveys. Deep field observations from Hubble, Spitzer, and ground-based telescopes showed nothing at the same coordinates, confirming that the object had been completely invisible until JWST's infrared sensitivity made detection possible. Its appearance only in the infrared bands confirmed the extreme redshift and supported the conclusion that it originated from a region of the universe previously unobservable. The discovery timeline was tightly documented. Initial detection occurred during routine Cosmos web scans. Automated software flagged the motion within days. Immediate re-observation confirmed the movement. Cross-checks with Hubble and ground-based instruments followed within weeks. ALMA and radio arrays conducted targeted scans to search for associated emissions. Data analysis continued over months, with astronomers running simulations and alternative calibrations to rule out errors. Each step strengthened the case that this was a real, moving object beyond conventional limits. Discussion among scientists considered the possibility of unknown cosmic phenomena. Could it be an intergalactic object traveling along an unseen filament of dark matter? Could it be an early-forming massive galaxy exhibiting unusual dynamics? Could it be a relic from an epoch of the universe never directly observed before? The data did not fit neatly into any existing category. Observers began referring to it as a truly anomalous detection, something no telescope had ever seen, and something that challenged assumptions about the cosmic frontier. The methods used to confirm the detection included repeated multi-epoch imaging, spectral analysis in multiple infrared bands, and cross-validation across instruments. JWST's precision pointing at L2 allowed weeks of continuous observation without interruptions, enabling the detection of minute shifts in position. The object's apparent motion could be quantified, showing consistent displacement over time and ruling out transient phenomena or observational errors. Even skeptics acknowledged the significance of the detection. The object's presence in infrared, its extreme redshift, and its motion suggested a phenomenon entirely outside normal observational boundaries. Alternative explanations, including instrumental glitches, cosmic rays, local objects, or lensing artifacts, failed to reproduce the observed motion when tested against the data. The anomaly resisted every attempt to explain it using conventional means. Astronomers continued to plan follow-up observations. JWST's deep field programs would revisit the coordinates at different intervals, building a timeline of motion. Other space-based infrared observatories, though less sensitive, were asked to provide supporting data. Ground-based facilities monitored the field for complementary optical or radio signals. The movement persisted, confirming that this was no isolated observation, but an actual object moving subtly yet undeniably beyond the observable universe. The detection also raised questions about cosmological models. If an object existed beyond the observable horizon and exhibited motion detectable by JWST, it implied that our understanding of the universe's structure, expansion, and boundary conditions might be incomplete. The observations prompted discussions about how matter could form and move outside known regions, how light could reach us across unimaginable distances, and whether other objects like it might exist, waiting for detection. The timeline of discovery highlighted the combination of infrared sensitivity, long exposures, and precise orbital stability that only JWST provides. Without infrared detection, the object would remain invisible behind cosmic dust and redshifted light. Without long, uninterrupted exposures, its subtle motion would be undetectable. Without precise instruments cooled to near absolute zero, its faint infrared signal would be lost in noise. The telescope captured data that revealed movement, spectral composition, and faint structure simultaneously, creating a comprehensive observation that no previous facility could achieve. This detection demonstrated the unprecedented capabilities of JWST. It could see extremely distant objects, measure their faint light, track subtle movement, and analyze spectral information all at once. Each piece of data reinforced the anomaly's authenticity. The object was neither noise, artifact, nor a misinterpretation. It was a real, moving source beyond the universe we thought we knew, revealed only because JWST could observe regions no other telescope could reach. The object continued to appear in repeated James Webb scans, its motion consistent across multiple epochs. Astronomers meticulously documented every exposure, every shift in position, and every spectral signature. Each piece of analysis added layers to understanding, yet questions remained unanswered. The movement itself was enigmatic. How could a structure exist outside the observable universe and still be detectable, with motion measurable across the scale of billions of light years? Observers had never recorded anything like it. Infrared redshift measurements remained central. Light from the object showed extreme stretching, placing it far beyond known galaxies. Observers compared these measurements with theoretical models, confirming that the light's journey spanned distances greater than the visible universe. The object's presence challenged assumptions about how and when matter can form, move, and remain observable. Every check reinforced its reality, and every check deepened the mystery. Even as attempts to replicate the detection with other observatories yielded no direct confirmation, JWST's data alone was compelling. The object moved across the sky in a measurable pattern, persisted over multiple exposures, and displayed infrared light consistent with distant matter. Astronomers could not explain it with conventional physics, instrumental errors, or known cosmic processes. Automated detection software, long exposure imaging, and repeated scans were crucial. Without these methods, the anomaly would have remained invisible, blending into the faint background glow of the early universe. Spectral analysis, infrared redshift, and careful multi-instrument cross-checks confirmed its presence, showing movement over time that no other telescope could have detected. The discovery timeline stretched over weeks and months. Initial detection, automated flagging, verification scans, cross-checks with Hubble, ground-based telescopes, ALMA, and radio arrays all contributed to confirming the anomaly. Alternative explanations were considered and systematically ruled out. The anomaly persisted, visible only to JWST, moving subtly across the sky and displaying characteristics no known object could replicate. Scientists began planning follow-ups. Deep field observations, spectral monitoring, and repeated positional tracking would continue over the coming months and years. The detection marked a turning point, highlighting the power of JWST to reveal objects that had previously been beyond human observation. The telescope was no longer just mapping galaxies or exoplanets. It had begun detecting phenomena that challenged fundamental assumptions about the universe's limits, physical and observational properties. The object detected by JWST immediately defied conventional understanding. Observers first noted its presence in the Cosmos Webb survey, where it appeared as a faint flickering point of light against a backdrop of galaxies, dust clouds, and the cosmic microwave background. Its location was extraordinary, calculations of its redshift placed it far beyond the limits of the observable universe. Standard cosmological models assume that beyond the cosmic horizon, no structured matter is detectable, that light cannot reach us from those regions. Yet here it was, a tangible point of infrared emission, arriving after traveling distances almost beyond comprehension. Infrared imaging revealed a glow that was faint but consistent. Unlike distant galaxies, whose light usually spreads over several pixels due to distance and redshift, this object remained unusually compact. The brightness, though extremely faint, was measurable with high confidence, and repeated exposures confirmed that the signal was real. Observers noted subtle variations in intensity across different infrared wavelengths. These variations hinted at the presence of ordinary matter, hydrogen and helium, possibly trace amounts of heavier elements, but the exact composition remained uncertain. Spectroscopy suggested a simple spectrum, dominated by low-energy infrared emission, consistent with an extremely cold object, perhaps a primordial galaxy or massive structure formed under conditions unlike anything previously observed. Movement was the property that caught the attention of astronomers worldwide. Over repeated exposures, the object shifted position ever so slightly against the backdrop of stationary distant galaxies. Automated detection software measured this motion with precision. It was slow in human terms, almost imperceptible when watching a single image, but measurable across days and weeks. The object's trajectory suggested motion relative to the cosmic microwave background, moving in a straight path across the survey field. Its speed, when translated from angular displacement to a cosmological frame, was astonishing, implying a velocity far greater than what galaxies normally achieve within clusters or cosmic filaments. The direction of motion did not correspond with known cosmic structures. Galaxies tend to follow patterns dictated by dark matter filaments, moving in clusters or along gravitational gradients. This object's path appeared isolated, moving independently of the surrounding cosmic web. Its trajectory was consistent over multiple exposures, ruling out observational artifacts, lensing distortions, or random errors in telescope pointing. Every measurement reinforced the reality of motion, suggesting a phenomenon entirely unlike anything previously catalogued. Infrared observations revealed additional clues about the object's nature. Its spectrum was dominated by long wavelength light, heavily redshifted by the expansion of the universe. Some bands showed hints of faint emission lines, potentially indicative of atomic hydrogen or helium. These lines, however, were weak and shifted far into the infrared, making identification challenging. Observers speculated that the faint lines could represent primordial material, gas that had never formed stars, or an early generation stellar system completely obscured in visible light. JWST's sensitivity allowed it to detect these faint signals, building a profile of an object that, until now, existed only in theoretical models. Brightness measurements over multiple exposures showed subtle variability. The object's luminosity was not constant. It flickered slightly across infrared wavelengths. Such flickering could indicate internal dynamics, perhaps star formation or interactions with nearby unseen matter. Alternatively, the variability could result from gravitational lensing by massive structures along the line of sight, though careful modeling suggested lensing alone could not fully explain the observations. Every measurement added to the mystery, showing that this was not a static point of light, but a living, dynamic object in some sense, moving and changing across space and time. The object's estimated distance placed it at extreme redshift, beyond the reach of previous telescopes. JWST's ability to detect infrared light allowed it to capture photons stretched by more than 10 billion years of cosmic expansion. The light reaching JWST was dim, traveling across regions of space that, according to standard models, should be largely empty or unobservable. Its very visibility suggested that the object was either extraordinarily luminous for its size or composed of material that radiates efficiently in infrared. Every detail of the observation challenged assumptions about what could exist at the edge of the universe. Observers noted the compactness of the object. Unlike distant galaxies, which spread out over the field of view, this point of light remained sharply defined, even after stacking multiple long-exposure images. This suggested a concentrated structure, potentially a single massive entity or a tightly bound group of primordial stars. Its physical size could not be measured directly, but modeling based on brightness and distance implied a scale far smaller than typical galaxies at comparable redshift. This compactness added to its enigmatic nature, hinting at formation processes completely unlike those observed in the early universe. Infrared measurements also provided indirect hints about temperature. The emission was extremely low energy, consistent with cold matter or low-temperature gas clouds. No high-energy signals were detected, no X-rays, no strong ultraviolet emissions, indicating that the object was not a quasar, black hole, or actively star-forming galaxy of conventional types. Its energy signature suggested a quiescent, possibly primordial structure, composed of hydrogen, helium, and minimal heavy elements. This aligned with theories of objects forming in the first few 100 million years after the Big Bang. Yet, the object's motion and visibility contradicted expectations for such distant matter. The motion itself suggested a unique frame of reference. Compared to the cosmic microwave background, the object's trajectory was linear, not bound by gravitational wells of nearby structures. Astronomers calculated its apparent speed in the cosmic frame, revealing velocities that would be extreme for any known matter in the early universe. Its movement appeared uncorrelated with nearby galaxies or clusters, traveling in a direction that did not match the flow of large-scale cosmic structures. This indicated either a previously unknown type of gravitational phenomenon or an entirely new class of cosmological object. Observational properties across multiple filters confirmed the consistency of the detection. Infrared bands from NIRCam and MIRI revealed a stable spectral signature despite slight flickering in brightness. The object's redshift remained extreme across different exposures, reinforcing the estimate of its location beyond the observable universe. Spectral energy distribution modeling suggested a low-temperature, low-density composition, potentially a cloud of primordial matter or a relic structure from the very early universe. Its spectral characteristics matched nothing previously observed in galaxies, stars, or nebulae. Brightness and flux measurements allowed astronomers to estimate its apparent magnitude. Though faint, the object was detectable at multiple wavelengths, demonstrating a persistent source of emission rather than a transient flare or artifact. Observers noted subtle color variations, potentially indicative of varying material composition or interaction with intervening intergalactic medium. These variations were weak but consistent, suggesting that the object's light was not purely uniform and may carry information about processes occurring within it or along its line of sight. Astronomers speculated about possible explanations. Could it be a primordial galaxy, one that formed stars much earlier than expected, traveling along a unique trajectory? Could it be a dense gas cloud, collapsing or moving under forces not yet understood? Could it be a relic of cosmic inflation, a structure pushed to extreme distance and exhibiting motion relative to surrounding space? Every property, location, motion, infrared signature, spectrum, challenged conventional ideas. The object refused to fit neatly into known categories, forcing scientists to consider entirely new possibilities. The object's motion also hinted at gravitational interactions. Even at extreme distance, its linear trajectory suggested that something was influencing its path, though no visible structure could account for it. Models of cosmic expansion and dark matter filaments were considered, yet none fully explained both the motion and infrared emission. Observers suggested that the object might represent a previously unobserved type of structure, potentially providing insight into hidden dynamics beyond the observable universe. Infrared brightness over time was key to understanding its nature. Long, continuous exposures allowed JWST to track subtle variations, revealing flickering that hinted at internal processes or interactions with unseen matter. Unlike stars or galaxies nearby, which show predictable patterns, this object's variability was unusual. It remained faint but persistent, detectable only in the most sensitive infrared measurements. Its stability and detection confirmed that it was real, not a processing artifact, and that it possessed physical properties capable of producing measurable infrared light across billions of light years. Spectral hints of composition suggested ordinary matter. Hydrogen and helium dominated, but the absence of heavier elements implied that the object was either primordial or formed under unusual conditions. Light absorption features were weak yet measurable, indicating the presence of cold gas rather than active star formation. Observers compared its spectrum to distant galaxies and early star clusters, finding similarities only in the simplest primordial models. Even then, the object's motion and compactness set it apart. JWST's observations across multiple instruments confirmed the anomaly. NIRCam provided high-resolution imaging, showing a sharply defined point of light. MIRI detected long-wavelength infrared emission, confirming extreme redshift and low temperature. Repeated exposures over days and weeks allowed measurement of motion and flux variations. Each instrument corroborated the others, producing a consistent, multi-dimensional profile of an object unlike any other. The object's location beyond the observable universe suggested photons had traveled farther than previously recorded. Infrared light stretched over extreme distances, carrying information from regions normally inaccessible. Its motion, spectral signature, brightness and compactness combined to create a detection that was both real and mysterious. Every measurement reinforced the reality of the object, yet none explained it fully. Observers modeled its possible mass, luminosity, and size, constrained by infrared flux and redshift. The object appeared unusually compact for its luminosity, hinting at either a dense primordial cluster or a single massive entity. Its motion could imply gravitational interactions with unseen matter, potentially a massive filament or halo beyond the observable universe. Its spectral properties suggested a quiescent object, emitting infrared light without active star formation. The mystery deepened as astronomers considered alternative explanations. Could it be a fragment of a massive early galaxy, ejected during gravitational interactions? Could it be a primordial star cluster, surviving intact across cosmic time? Could it be evidence of previously unknown processes during inflation or the early expansion of space? None of these hypotheses fully explained the observed properties. Its location, motion, compactness, and infrared signature formed a puzzle that resisted conventional solutions. Even slight variability in infrared flux provided clues. Observers suggested that flickering could indicate internal dynamics, perhaps rotation, heating, or subtle interactions with background matter. Yet the timescales and amplitude of variation were unusual, inconsistent with ordinary galactic or stellar processes. Continuous tracking allowed scientists to measure these variations accurately, confirming that the anomaly was a persistent and evolving source. The Hubble's law expansion predictions. From the first moment astronomers noticed its motion, it was clear that this object was unlike anything they had ever seen. JWST had revealed countless distant galaxies, star clusters, and faint glimmers of the early universe, but nothing behaved like this. Its movement across the sky didn't match what anyone expected based on Hubble's law, the fundamental rule that galaxies recede from us at speeds proportional to their distance. Every galaxy, every cluster observed before followed a predictable pattern. The farther away it was, the faster it appeared to move away due to the expansion of space itself. This object, however, didn't follow that rule. In repeated observations, astronomers calculated its apparent velocity relative to the cosmic background. The numbers were staggering. If you tried to interpret its motion in the simplest way, it looked as though the object was moving faster than light. And yet, according to the rules of physics, nothing can exceed the speed of light locally. The solution, cosmologists explained, was subtle. The object wasn't really breaking physics. Its apparent superluminal motion is an illusion caused by the expansion of space itself. Space is stretching, carrying light and matter with it. At extreme distances, this stretching can make objects appear to move faster than light relative to us, even though they are obeying the laws of physics in their own frame. This apparent speed is mind-bending. Imagine standing on a vast plain and seeing a distant hill slowly drift away. Now imagine the plane itself is expanding faster than you can walk, stretching the distance between you and the hill. From your perspective, the hill seems to rush away at impossible speed, even though it's not moving through the plane itself. That's essentially what is happening with this JWST object. Except the plane is the fabric of space itself, stretching across billions of light years. But this object was even stranger than simple expansion effects could explain. Its trajectory didn't match the motion of nearby galaxies. Normally, galaxies move along the gravitational currents of the cosmic web, flowing along dark matter filaments like leaves on a river. This object, however, seemed to carve its own path, almost as if it were independent of these cosmic flows. Its motion relative to the cosmic background was consistent, straight, and unbending, while neighboring galaxies followed the expected patterns dictated by gravity and expansion. The brightness and redshift added another layer to the mystery. Light from the object was so redshifted that it implied extreme distance, beyond what we can directly observe, yet it was still visible. Normally, objects that distant are either too faint or too diffuse for our telescopes to detect. JWST's infrared eyes captured its faint glow, revealing a structure that shouldn't even be observable. Combined with its apparent motion, this made astronomers scratch their heads. How could something so far away, beyond the reach of Hubble, not only be visible, but also move in such a distinct, measurable way? Some scientists likened the object's behavior to a ghost in the cosmos. It's as if it exists on the edge of our universe, obeying laws that we understand in theory but rarely witness in practice. Its apparent speed is not about moving through space faster than light. It's about space itself carrying it along, stretching and bending our perception of motion. The further away the object is, the more extreme this effect becomes, and this particular object sits at a distance where those effects are pushed to the limit. Astronomers double-checked everything. Could it be a lensing effect, a trick of gravity bending light from another source? Could it be a local object masquerading as a distant one? Each alternative fell short. Lens distortions produce arcs, duplicated images, or smeared structures, none of which matched the clear, compact appearance of this point of light. Local objects, such as dwarf stars or asteroids, move differently, with trajectories governed by our own galaxy's gravity, not the motion of the universe at large. Nothing explained the combination of extreme distance, apparent speed, and clear movement across the sky. The object's direction of motion was particularly puzzling. Galaxies receding due to cosmic expansion generally move radially away from us, spreading outward in all directions. This object's movement, however, had a tangential component, shifting across our field of view in a way that suggested real motion relative to the surrounding cosmic backdrop. It was not just receding, it was traveling sideways, against a framework that should have constrained its path. That sideways motion, combined with the apparent speed from expansion, produced a truly unusual signature, an effect no previous telescope had recorded. Spectral analysis provided additional clues. Infrared observations showed that the object's light was stretched across wavelengths consistent with extreme distance. Its apparent motion corresponded to shifts in redshift across the observation period, suggesting that some of its light was being altered not by local motion, but by the underlying dynamics of space itself. Cosmologists noted that the stretching of light, combined with angular movement, could produce the illusion of superluminal travel, but the exact combination seen here was unprecedented. The apparent superluminal motion doesn't break relativity, but it challenges intuition. We're used to thinking of speed as simple movement through space. At cosmic scales, speed becomes relative, entangled with the expansion of space itself. At distances approaching the edge of the observable universe, Small motions in the object's frame, combined with the stretching of space, can create astonishing apparent velocities. That is what astronomers are seeing here. JWST's repeated measurements confirmed it. The object is real, distant, moving, and displaying the maximum possible effects of cosmic expansion. This also implies that the object is extraordinarily old. Light reaching JWST has traveled billions of years. By the time the photons were captured, the universe was barely a few 100 million years old. Whatever the object is, galaxy, cluster, or something else, it existed in the earliest epochs of cosmic history, moving along a path determined not just by gravity, but by the expansion of space itself. Its apparent motion tells us that the universe is more dynamic and strange than models predicted. Nearby galaxies in the same deep field followed predictable Hubble law expansion patterns. Their speed away from Earth increased proportionally with distance. This object ignored that pattern. Its tangential motion across the sky, combined with extreme redshift, created a velocity signature that doesn't fit conventional expansion curves. It's a reminder that, at the edge of the universe, ordinary rules break down, or at least appear different to observers bound within the cosmic horizon. Observers use simulations to understand the effect. Models of cosmic expansion showed that an object at this distance, with slight intrinsic motion, would appear to move across the sky at an impossible speed. Its tangential displacement over weeks of observation corresponded to billions of light-years of travel, a number that seems absurd but is fully consistent with relativistic cosmology. The apparent superluminal motion is a result of geometry, expansion, and distance, real physics, but operating at a scale far beyond human intuition. Even the simplest visual representation is mind-blowing. Imagine a tiny dot moving slowly in a telescope image. You track it over days, then weeks. Its movement seems small, but when converted into cosmic distances, that small shift corresponds to speed billions of times faster than anything humans could imagine. That's the paradox of observing at the edge of the universe. JWST's instruments capture these tiny angular changes with incredible precision, and the data reveal movement that is real, measurable, and utterly alien. Another striking feature is the independence of its motion. Cosmic structures tend to flow along the cosmic web. Galaxies cluster, merge, and move together along gravitational paths. This object seems free from that web. Its straight trajectory, unaffected by nearby structures, suggests it is isolated, moving along a path unconstrained by the familiar patterns of cosmic gravity. That isolation, combined with extreme distance, makes it one of the most mysterious objects ever observed. Astronomers also measured the apparent acceleration of the object. Over weeks of repeated exposures, its speed remained roughly constant relative to the cosmic background. There was no obvious deceleration or deviation caused by nearby gravitational fields. This constancy is part of what makes it so unusual. Normally, galaxies exhibit subtle velocity changes as they interact with local clusters and filaments. Here, the object moves like a ghost, unaffected by known structures, carried along only by the expansion of space and possibly its own intrinsic motion. Spectral data provided hints about its composition, though faint. The infrared signature suggests cold, primordial matter with low, heavy element content. The combination of distance, motion, and spectral simplicity reinforces the idea that this is an extremely early structure. Unlike ordinary galaxies, it lacks obvious star formation, glowing clusters, or bright cores. Yet it moves, interacts with expansion, and produces measurable light, making it a tangible but alien presence. The apparent superluminal motion has become a central topic of discussion among cosmologists. Some theorists suggest that the object may be part of a population of early universe structures that we have never observed before. Others propose more exotic ideas, including interactions with hidden regions beyond the observable horizon, or influences from unknown forms of dark matter or energy. Every theory is constrained by the need to match JWST's precise measurements: extreme distance, tangential motion, compact infrared signature, and spectral simplicity. Repeated JWST observations continue to track its motion. Each exposure reinforces the anomaly. Its trajectory remains straight and consistent. Apparent speed remains high. Infrared flux remains faint but stable. Observers are watching in real time as the edge of the observable universe reveals behavior that is fully consistent with cosmological expansion, yet completely beyond intuition. Even casual viewers can imagine the scene, a faint dot moving slowly across a deep field image. Week after week, it shifts imperceptibly, yet, when translated into cosmic distances, the motion corresponds to something extraordinary, almost supernatural in scale. That is the reality of observing the universe at its extremes. JWST does not just see distant light, it measures the dynamics of space itself. This object challenges expectations at every level. Hubble law expansion predicts a uniform recession velocity, yet here is a point moving tangentially, apparently faster than light in our frame, visible due to its infrared emission. It is isolated, compact, faint, cold, and dynamic. It exists at a distance and under conditions where conventional astrophysics has little to say. Every piece of data collected reinforces that the universe is stranger than previously imagined, and JWST is finally showing it to us in vivid detail. Speculative categories. The moment astronomers confirmed the anomaly, the first question was unavoidable. What could it be? The object doesn't fit neatly into anything we know. Its location beyond the observable universe, its apparent motion, and its faint infrared glow make it one of the strangest detections in cosmic history. Naturally, speculation has raced ahead of explanation. One possibility is that this object is a rogue galaxy or cluster outside the observable bubble. Imagine a galaxy so far away that it lies beyond the horizon of what we can normally detect, drifting through regions of space unseen by conventional telescopes. Unlike typical galaxies, which are bound to clusters and filaments, a rogue galaxy could move independently, carried by the expansion of space and its own gravitational momentum. Its infrared signature suggests that it could be composed of primordial gas and early-generation stars, compact yet luminous enough for JWST to detect. Its apparent superluminal motion could result from both the stretching of space and the unusual path of a galaxy unbound from nearby structures, moving like a lone ship in the cosmic ocean. A rogue cluster would magnify the mystery even further. Clusters are massive collections of galaxies bound together by gravity and dark matter. If this were a cluster beyond our observable horizon, it could represent an entire unseen population of early cosmic structures. Such a cluster would emit faint infrared light from its member galaxies, yet still appear as a single point due to distance. Its movement would reflect collective dynamics, potentially revealing interactions with dark matter or hidden gravitational currents. A rogue cluster would challenge the assumption that structure formation is limited to the visible universe, suggesting that massive objects exist in places we previously thought were empty. Another speculative category is an exotic object, something unlike conventional galaxies or clusters. Astronomers have considered the possibility of a hypermassive black hole, a gravitational monster millions or even billions of times the mass of our Sun, surrounded by a faint accretion disk of dust and gas. Such an object could emit infrared radiation as matter slowly falls into it, producing a faint but detectable glow. Its apparent motion might arise from gravitational interactions or even subtle ejections of energy along jets, though the observed straight-line trajectory makes conventional black hole motion unusual. A hypermassive black hole beyond the observable universe would be unprecedented, offering a window into extreme conditions during the earliest epochs of cosmic history. Energy jets are another candidate in the exotic category. Active galactic nuclei in the local universe often produce jets of matter traveling at near-light speed, emitting radiation across multiple wavelengths. If this object were a jet from a massive black hole or another exotic source beyond the observable horizon, JWST could detect its infrared emission, while optical and X-ray light remain hidden by redshift. The apparent motion across the sky could reflect the jet's angle relative to Earth, combined with the stretching of space over billions of years. Such a scenario would be unique, revealing the behavior of high-energy phenomena in the most remote corners of the universe. Finally, the most speculative category involves artifacts of unknown physics. Some theorists have suggested that objects like this might represent multiverse collisions, where our universe interacts with a neighboring bubble universe. Such interactions could leave behind isolated structures, faint but detectable, moving in ways that violate conventional Hubble flow. JWST's observations provide a tantalizing glimpse into possibilities beyond standard cosmology, hinting that the object could be a remnant of physics we have not yet measured or understood. Another unknown physics scenario involves primordial universe remnants, structures formed in the moments immediately after the Big Bang that somehow survived to the present. These could be dense knots of gas, exotic particle clouds, or even compact collections of early dark matter. Their motion could reflect forces from the earliest epochs, combined with the expansion of space, producing the unusual trajectory and apparent superluminal effects seen by JWST. Observing such remnants would be like looking at a living fossil of the cosmos, a direct connection to the universe's birth. Each of these categories carries its own questions and implications. A rogue galaxy suggests uncharted territory beyond our visible bubble. A hypermassive black hole or energy jet pushes the limits of high-energy physics and early structure formation. Unknown physics artifacts hint at interactions or remnants that challenge every assumption about the universe's origin and dynamics. Astronomers are careful, knowing that speculation must eventually meet observation. JWST's data provide the first clues: location, motion, infrared signature, but cannot yet definitively categorize the object. Every model must account for its extreme redshift, compact appearance, apparent motion across the sky, and faint but consistent infrared emission. Each speculative scenario can explain some aspects, but none explains all of them simultaneously. The rogue galaxy or cluster hypothesis relies on conventional physics, but stretches the limits of distance and isolation. Exotic objects push known astrophysical mechanisms to extremes, imagining massive black holes or energy jets moving in unexpected ways. Unknown physics categories explore possibilities that are theoretical but not yet observed, hinting at the possibility that the universe contains features outside our standard cosmological understanding. JWST's ability to detect this object is key to exploring all these possibilities. Its long exposures and infrared sensitivity allow astronomers to see faint light that has traveled billions of years. Its stable orbit at L2 lets it measure subtle motion with unprecedented accuracy, capturing changes that other telescopes could never detect. Each observation adds detail to the profile of the object, informing speculation and testing hypotheses about its nature. Even within the rogue galaxy category, the object is unusual. It is compact, emitting a faint infrared glow without obvious star clusters or optical components. Its motion is straight and persistent, unlike galaxies caught in cluster dynamics. This independence suggests a formation or evolutionary path that is not captured in current models, hinting at structures forming beyond the observable horizon, traveling along paths unbound by typical gravitational flows. Exotic objects, on the other hand, emphasize energy processes. A hypermassive black hole could produce faint infrared emission from dust heated by gravitational energy. Jets could project energy across vast distances, their light stretched by redshift into infrared bands. The combination of extreme distance and straight-line motion makes either scenario highly unusual, requiring conditions rarely considered in early universe models. Unknown physics scenarios open the door to ideas that challenge conventional observation entirely. Multiverse collisions, for example, suggest that isolated patches of matter could appear beyond the observable universe, moving in ways inconsistent with local expansion. Primordial remnants hint at survival of early structures that conventional cosmology predicts should have been disrupted or dispersed. JWST's data may be the first empirical glimpse of these possibilities, making the object a potential portal into entirely new branches of physics. Astronomers continue to monitor its motion. Every additional exposure allows them to refine measurements, track angular displacement, and analyze spectral features. Simulations test how different models, rogue galaxy, hypermassive black hole, primordial remnant, would appear under JWST's instruments. None matches perfectly, highlighting that the object exists at the edge of our understanding, teasing the boundary between observation and speculation. Brightness and infrared spectrum remain critical. Its faint red-shifted glow indicates a cold, distant structure. Variations are minor but consistent, suggesting an object that is persistent yet subtle. Models of rogue clusters, energy jets, and primordial remnants all predict some form of emission, but the particular combination of compactness, motion, and spectrum remains unique. JWST provides the only window into this behavior, capturing details invisible to every other telescope. Each speculative category also carries implications for cosmology. A rogue galaxy could indicate that large structures exist beyond the observable bubble, expanding the horizon of detectable matter. Exotic objects could reveal mechanisms of energy and mass in extreme conditions, pushing the limits of what early galaxies and black holes could achieve. Unknown physics artifacts hint that the universe may hold structures and processes entirely unaccounted for, suggesting that JWST is finally revealing a layer of reality previously imagined only in theory. Science behind the motion. Cosmology basics. When you look up at the night sky, it's easy to imagine space as calm, static, and endless. But the universe is not still, it's expanding. Space itself is stretching, carrying galaxies and clusters along with it. This expansion is subtle nearby, barely noticeable across human lifetimes. But across billions of light years, it becomes dramatic. Galaxies at the far edge of the universe appear to be moving away from us at incredible speeds. This expansion is the foundation of modern cosmology and the key to understanding distant objects like the one JWST detected. Expansion means that the distance between objects in space grows over time. It's not that galaxies are moving through space like cars on a highway. The space between them is stretching. Imagine dots painted on a balloon. As the balloon inflates, the dots move apart, not because they are driving anywhere, but because the surface of the balloon itself is expanding. In the universe, this stretching of space happens in all directions, and it affects everything, including the light traveling toward Earth. Light traveling through an expanding universe experiences redshift. The wavelength of light stretches along with space. The further a galaxy is, the more its light shifts toward the red end of the spectrum. This is why the most distant galaxies JWST can see appear in infrared, even though they may have originally emitted visible or ultraviolet light billions of years ago. Redshift is both a measure of distance and a clock, telling us how far back in time the light originated. The higher the redshift, the further the galaxy, and the closer we are to seeing the universe in its infancy. The cosmic horizon defines the edge of what we can observe. Light from objects beyond that horizon hasn't had time to reach us since the Big Bang. The universe is roughly 13.8 billion years old, so there's a limit to how far we can see, a boundary called the observable universe. JWST cannot literally see beyond that horizon. There is no telescope powerful enough to capture light that has not yet arrived. But JWST can detect objects at the very edge, pushing our vision to the limits of the observable universe. Its extreme infrared sensitivity allows it to capture faint photons from billions of light years away, revealing structures formed in the universe's earliest moments. The difference between observable and unobservable universe is subtle but critical. Beyond the cosmic horizon, objects may exist, but their light hasn't reached us yet. That means JWST isn't looking beyond the universe. It's looking at the most distant reaches of the universe that can ever be observed. Objects at this edge appear faint, stretched, and slow-moving in human perception, but their actual behavior may be astonishing when corrected for cosmic expansion. JWST's ability to detect these objects relies on several features. Its long-exposure infrared imaging captures photons that have traveled across billions of years of expanding space. Its stability in orbit at the L2 point allows uninterrupted observation, crucial for detecting faint, distant light that would otherwise be lost to the background. By combining multiple exposures and carefully analyzing redshift, astronomers can build a picture of objects at the very limits of observability, teasing out motion, brightness, and spectral features. Understanding expansion and redshift helps explain why the JWST object appears to move unusually fast. Space stretching between us and the object amplifies apparent motion, a phenomenon called apparent superluminal motion. From Earth's perspective, the object seems to travel faster than light, even though it obeys the laws of physics locally. Its redshift shows that its light originated billions of years ago, and the expansion of space has stretched both the light and its apparent trajectory. Observing this effect requires an understanding of the cosmos on its largest scales, where intuition about speed and distance breaks down. At the edge of the observable universe, galaxies behave differently from those nearby. Their light is faint, highly redshifted, and delayed by billions of years. What JWST detects is not just a snapshot of position, it's a record of history. Observing the most distant galaxies means looking back to a time when the universe was a fraction of its current age. These early objects are the first galaxies, star clusters, and possibly rogue structures formed before most of the universe even existed as we know it. JWST can probe these extreme distances because of infrared transparency. Dust and gas in the universe scatter visible light, obscuring distant objects. Infrared light, however, penetrates cosmic dust, allowing JWST to see faint sources previously hidden. This capability lets astronomers detect not only the light from early galaxies, but also anomalous objects that appear to move or behave unusually, like the one beyond the observable edge. The cosmic horizon is not a physical wall, it's a boundary defined by time and the speed of light. Beyond it, galaxies may exist, but their light hasn't had time to reach us. JWST observes the photons that have arrived from the farthest reaches, constructing a map of the early universe. This map reveals galaxies forming, clusters interacting, and rare anomalies appearing as tiny points of light. The most extreme objects may seem to defy conventional rules, like moving faster than expected, because the expansion of space affects how we perceive motion. Redshift is not just about distance, it is also about time. Observing high redshift objects lets astronomers study the universe as it was billions of years ago. The JWST object shows redshift so extreme that its light originated when the universe was less than 1 billion years old. That light carries information about composition, temperature, and movement, compressed into the faint infrared glow detected today. By analyzing redshift and motion together, astronomers can infer not only distance, but also apparent velocity, revealing phenomena like tangential drift and apparent superluminal motion. JWST's observations remind us that the universe is dynamic. Expansion stretches distances, redshift shifts light, and the cosmic horizon limits what can be seen. Yet within these limits, the telescope captures an incredible range of phenomena. From the first galaxies to rogue objects at the very edge, JWST shows the universe in motion, not static. Every photon tells a story of cosmic evolution, of space stretching, of light traveling across billions of years, and of objects moving in ways that challenge human intuition. Even though JWST cannot literally see beyond the universe, it can reveal objects that exist at the boundary of what is visible. That boundary is where light has traveled the longest, where redshift is extreme, and where motion appears strange. The telescope captures faint signals, reconstructing trajectories, brightness, and spectra that reveal the underlying physics. Objects that appear anomalous, like the moving point detected in the deep field, can be measured with precision, giving insight into the interplay of expansion, distance, and redshift. The expansion of the universe also affects the apparent shape and distribution of distant objects. Galaxies at extreme redshift appear stretched and faint, sometimes distorted by gravitational lensing. JWST's high-resolution infrared imaging separates these distortions from real motion, allowing astronomers to track anomalies accurately. This makes it possible to identify individual points of light that move across the sky in ways conventional models would not predict. Understanding the difference between observable and unobservable regions is crucial when interpreting JWST data. The observable universe contains all the light that has reached us since the Big Bang. Beyond that, there may be vast structures, voids, or entire clusters, but their light has not arrived. When JWST detects an object at the extreme edge, it is seeing the very last light that could ever reach us from that distance. Apparent motion, brightness, and redshift all combine to create signals that appear almost impossible, yet are grounded in real cosmology. Infrared detection, long exposures, and stable orbit at L2 make JWST uniquely capable of revealing these edge-of-universe phenomena. Other telescopes like Hubble could glimpse faint galaxies, but the extreme redshift and faint infrared flux of the JWST object require the telescope's unmatched sensitivity. This capability allows astronomers to push the limits of observation, identifying motion, composition, and structure in a region where conventional rules about galaxies, clusters, and expansion appear to break down. Physics of motion. At the edge of the observable universe, motion does not behave the way we intuitively expect. A galaxy here on Earth moves in ways we can measure directly, influenced by gravity, momentum, and local interactions. But for objects billions of light years away, the rules look very different. Their apparent motion is shaped not only by their own movement, but by the expansion of space itself, subtle gravitational effects, and the bending of light along their path. Observing them requires understanding how extreme redshift changes perception. When light travels across billions of years of expanding space, it carries with it the story of motion, encoded in tiny positional shifts, wavelength changes, and brightness variations. In extreme redshift scenarios, even small intrinsic motions of an object can translate into large apparent displacements across the sky. Space itself stretches, and light traveling through it is stretched along with it. This means that the object's angular position in the sky can shift over time, creating the appearance of motion that is amplified compared to what would be expected at nearby distances. Gravitational lensing adds another layer of complexity. Mass bends space, and light passing near massive structures like clusters of galaxies is deflected along curved paths. A distant object behind such a lens may appear distorted, magnified, or even duplicated. The apparent motion of the object can be influenced by the relative motion of the lensing mass itself. A subtle drift in the lensing cluster can make a distant object appear to move across the sky. JWST can detect these minute shifts, separating real motion from lensing artifacts using repeated observations and careful modeling. Cosmic expansion dominates the apparent motion at extreme distances. Galaxies are not moving through space faster than light. Rather, the space between them and Earth is stretching. For objects at extreme redshift, the expansion is so strong that small intrinsic movements are magnified into what looks like superluminal motion. This apparent motion is a product of geometry, distance, and time. Light emitted billions of years ago reaches our telescope with angular shifts that map to huge apparent speeds, even though locally the object obeys all physical laws. Peculiar velocities also play a role. Every galaxy has its own motion relative to the cosmic background, driven by gravity from nearby structures, interactions, and dark matter flows. In nearby space, these velocities are small compared to overall expansion, but at extreme distances, their effects combine with redshift and expansion in unusual ways. A tiny intrinsic sideways movement can appear amplified across billions of light years, producing trajectories that seem inconsistent with standard Hubble law expansion. The interplay of these factors is crucial for understanding JWST's observations. Apparent motion at extreme redshift is never a simple translation of local velocity. It results from a combination of intrinsic movement, expansion of space, and the bending of light by gravitational masses along the line of sight. Infrared imaging and repeated long exposures allow astronomers to track subtle positional changes, revealing motion that would otherwise be invisible. Gravitational lensing can also magnify faint objects, making them detectable at the very edge of the observable universe. Lenses can act as natural telescopes, stretching light into arcs or brightening faint points. This magnification allows JWST to measure positional shifts that indicate motion. Careful analysis distinguishes between shifts caused by lensing and shifts caused by the object's intrinsic motion through expanding space. Cosmic expansion creates apparent superluminal effects, where the object seems to move faster than light. This is not a violation of physics. It is a geometric result of observing light traveling across a stretching universe. For objects at extreme redshift, the further away they are, the faster they appear to move in our frame. JWST's precision allows these apparent velocities to be measured, providing clues about the distance, intrinsic motion, and interactions of the object. Peculiar velocities, when combined with extreme redshift, create patterns of movement that challenge intuition. Slight deviations from radial expansion produce angular changes that are detectable over weeks, months, or years of observation. JWST's stability and infrared sensitivity make these tiny shifts visible, translating them into measurable trajectories. The telescope captures motion encoded in photons that began their journey billions of years ago, allowing astronomers to reconstruct the object's path across both space and time. Observing motion at extreme redshift also requires understanding the frame of reference. From Earth, we measure motion relative to the cosmic microwave background. At great distances, the light we see is influenced not only by intrinsic motion and local gravity, but also by the large-scale flow of space itself. This means that apparent motion is a combination of multiple layers: the object's movement, the stretching of space, lensing distortions, and interactions with local gravitational fields along the line of sight. JWST can separate these layers by combining repeated imaging, spectroscopy, and angular analysis. The effect of these combined forces is dramatic. A point of light billions of light years away may appear to drift across the sky over time, seemingly faster than any galaxy in the local universe. Its trajectory can be straight, curved, or distorted, depending on gravitational influences. Motion appears in ways that seem impossible without understanding the underlying cosmology, but with redshift, expansion, lensing, and peculiar velocities accounted for, it becomes predictable, though still astonishing. Even in simple terms, the physics of motion at the edge of the universe is counterintuitive. A small sideways movement at extreme distance can translate into enormous apparent displacement. The faster space expands, the more pronounced this effect becomes. Gravitational lensing can bend paths, magnify light, or create illusions of duplicate objects. Peculiar velocities introduce additional shifts, and redshift stretches every wavelength, translating early universe dynamics into infrared light that JWST detects today. JWST's observations make it possible to quantify these effects. Repeated scans measure angular displacement, allowing astronomers to calculate apparent velocities and compare them to models of cosmic expansion. Infrared spectra reveal redshift, confirming distance and helping separate intrinsic motion from expansion effects. Gravitational lensing models account for deflections along the line of sight. Together, these analyses reveal an object moving in a way that is both extraordinary and consistent with known physics, filtered through the lens of extreme redshift. The physics of motion in this regime highlights the limits of human intuition. Nearby galaxies move slowly and predictably. Objects at extreme redshift behave differently, their apparent velocities shaped by space itself. JWST captures these motions with precision, transforming tiny positional shifts into insights about expansion, structure, and the dynamics of the early universe. Each observation combines cosmic geometry, gravitational influence, and intrinsic motion into a single measurable signal, revealing phenomena no other telescope could detect. Motion at extreme redshift is also time-encoded. Light takes billions of years to reach us. The apparent movement we measure today reflects the object's path long ago. Observed shifts combine ancient motion with billions of years of cosmic expansion, producing trajectories that seem impossible in human terms but are fully consistent with cosmology. JWST transforms these faint ancient signals into data, showing motion as a tangible, measurable property rather than a theoretical prediction. Gravitational lensing and cosmic expansion can amplify apparent motion, creating what looks like acceleration or sudden directional changes. Peculiar velocities introduce small deviations that become significant over cosmic scales. JWST's infrared observations, combined with repeated long exposures, allow astronomers to detect these nuances. Every photon tells a story of movement, influenced by both local forces and the stretching of the universe itself. Theoretical implications. The JWST object isn't just unusual, it bends the rules of what cosmologists expect. At the edge of the observable universe, every galaxy, cluster, and luminous structure follows a pattern dictated by the LCDM model, the standard framework describing the cosmos. Galaxies drift apart as space expands, clustering along filaments of dark matter, forming a vast cosmic web. Distances, velocities, and redshifts align with predictions. Then this object appears. Its motion, location, and characteristics hint at something beyond ordinary expectations. Some of the first questions focus on LCDM itself. This model has successfully explained cosmic microwave background fluctuations, galaxy distributions, and large-scale structure growth for decades. Yet here is an object whose apparent trajectory doesn't fit neatly. It seems to move independently of surrounding structures, ignoring the gravitational currents that guide neighboring galaxies. Its apparent superluminal motion, combined with extreme distance, test the limits of what LCDM predicts. It doesn't outright break physics, but it forces theorists to examine edge cases and extreme cosmic environments, places where the model has never been tested directly before. The object could indicate cosmic void flows, large regions of space nearly empty of galaxies, stretching across hundreds of millions of light-years. In these voids, the expansion of space dominates over gravitational clustering, and matter can move in unusual ways. A structure at the boundary of a void might appear to drift faster, even tangentially, compared to standard expectations. JWST's detection may represent one of the first glimpses of motion in these extreme cosmic deserts. The object's straight, persistent path across the sky could map the flow of matter in ways not visible with previous telescopes, revealing hidden currents, shaping the universe's evolution. Other possibilities point to large-scale structure anomalies. The cosmic web is expected to form patterns, filaments, nodes, and clusters aligned with dark matter. A lone object like this, appearing beyond typical filamentary connections, could mark a rare fluctuation in the universe's structure. Perhaps it originated in a region unusually devoid of matter, allowing it to move unimpeded for billions of years. Or perhaps it is part of a hidden filament extending into the unobservable universe, stretching the web beyond our current observational limits. Either scenario challenges assumptions about uniformity and randomness at extreme scales. Speculation also extends to more exotic physics. Some theorists suggest that anomalies like this could be hints of a multiverse. If the universe is one bubble among many, interactions at the boundaries might leave traces in the form of isolated structures, faint but observable. These structures might drift or move in ways inconsistent with the rest of the cosmic web, appearing almost like ghosts from another realm. JWST could be capturing one of the first tangible signs that the universe is not isolated, that our observable patch is connected or collided with something beyond. Hints of the primordial universe may also play a role. Extreme redshift means the object existed when the cosmos was very young, less than 1 billion years old. Its apparent independence from surrounding gravitational structures raises the possibility of surviving primordial remnants, matter that formed in the very first moments after the Big Bang and persisted largely untouched. These ancient structures could move along trajectories set in those earliest epochs, producing signals that today appear anomalous but are consistent with ancient dynamics. Large-scale flows and anomalies could redefine how astronomers measure expansion. The object's tangential movement suggests that the universe may contain hidden currents or regions where expansion behaves differently than in denser clusters. These flows could influence galaxy formation, clustering, and even the propagation of light over billions of years. JWST is providing a first look at these dynamics, revealing that the universe at extreme distances is not a uniform, featureless expanse, but a rich, dynamic environment with motion that challenges standard models. Theoretical models must also account for the apparent superluminal motion. While expansion explains much, the combination of distance, motion, and isolation is extreme. Simulations using LCDM assumptions struggle to reproduce an object with this combination of redshift, velocity, and tangential trajectory. This doesn't imply a failure of the model at small scales, but it highlights the need to explore new parameters or consider edge case physics in the early universe. Some researchers propose that this object could be part of dark matter or dark energy anomalies. Large-scale motion may be influenced by unseen forces or distributions of matter. If regions of space contain concentrations of dark matter or variations in dark energy density, structures might move in unexpected ways. JWST's detection may provide one of the first observational handles on these hidden components, showing how they sculpt motion on cosmic scales. The object's extreme distance also raises questions about early structure formation. At this redshift, conventional galaxy formation models suggest that massive structures should be rare, still in the process of collapsing from primordial fluctuations. Yet this object appears compact and coherent, already moving through space with a defined trajectory. This could imply that our understanding of early structure growth is incomplete, that rare objects formed faster or differently than predicted. Even small discrepancies between prediction and observation become amplified at these distances. JWST can track tiny angular shifts and faint infrared fluxes, translating them into apparent motion and dynamics. Every photon carries information about the universe's expansion, gravitational landscape, and hidden structures. Observing something like this object challenges theorists to reconcile extreme motion, isolation, and redshift within existing frameworks, or to consider entirely new mechanisms. Hints of a multiverse or unknown physics are speculative, but grounded in observation. The object's trajectory, apparent speed, and distance push the boundaries of what LCDM describes. It may be an extreme but plausible fluctuation, or it may represent a phenomenon that requires extending theory. Cosmic void flows, primordial remnants, hidden filaments, or multiverse interactions. Any could explain some features. Each scenario would reshape the way astronomers think about the large-scale universe, showing that the cosmos at its edge behaves in ways only now becoming observable. JWST's ability to detect motion, redshift, and structure at these scales opens a window into previously inaccessible regions. Theoretical implications are enormous. If other objects like this appear, patterns might emerge, revealing new flows, structures, or interactions. Each detection builds a map, not just of light, but of motion across space and time, hinting at cosmic dynamics invisible until now. This object may remain unique, or it may be the first of many. Its trajectory and speed, when combined with deep field observations, could uncover anomalies in the universe's expansion rate, unexpected flows in cosmic voids, or even remnants of multiverse collisions. JWST doesn't just see farther, it measures the universe's motion at the limits of observability, translating tiny shifts in photons into profound theoretical challenges. Comparison with other cosmic anomalies. The universe has always been a place full of surprises. and over the decades, astronomers have catalogued anomalies that defied expectations. Some were strange points of light, some were shifts in motion, others were subtle temperature variations across the sky. Each time, scientists were forced to pause, to double-check their instruments, to question assumptions, and to confront the possibility that the cosmos didn't always follow the rules we thought it did. One of the first to grab global attention was Tabby's star. Officially called KIC 8462852, it flickered in ways that made no sense. Stars typically shine steadily, perhaps with minor variations due to spots or pulsations. Tabby's star dimmed dramatically and irregularly. At first, astronomers considered every possibility: dust clouds, instrumental errors, even alien megastructures. Over time, models suggested clumps of dust or unusual debris could explain the dimming, yet some aspects remain unexplained. The star taught the world that even nearby stars could behave in ways that defied conventional expectations. Then there was Oumuamua, the mysterious interstellar visitor. Detected in 2017, this elongated object zipped through our solar system at incredible speed, following a path that suggested it came from outside the Sun's gravitational influence. Its shape, motion, and acceleration confounded astronomers. Natural explanations like outgassing were proposed, but the lack of a visible cometary tail left questions unresolved. It was a fleeting mystery, a cosmic ghost passing through, reminding observers that even a small object could carry profound surprises from the galaxy beyond. The Great Attractor revealed something larger and more subtle. Deep in the zone of avoidance, where the Milky Way obscures distant light, astronomers noticed galaxies collectively moving toward a region in the sky with no visible source. Gravity from something massive was pulling entire clusters, suggesting structures hidden beyond our sight. It forced scientists to map mass indirectly, using velocities rather than light, showing that not all cosmic influence is visible. Even today, the Great Attractor stands as a reminder that the universe contains forces that are detectable not through direct observation, but through motion and interaction. Dark flow added another layer of mystery. Some galaxy clusters appeared to drift in a common direction, inconsistent with local expansion. These motions suggested influences from regions beyond the observable universe. While some studies questioned the strength or even the existence of dark flow, the idea that distant, unseen mass could move matter in measurable ways captured imaginations and challenged cosmological assumptions. It showed that large-scale motions could hint at the unknown, revealing patterns invisible to casual observation. The cosmic microwave background cold spots were anomalies of a different kind. Tiny variations in temperature, some colder than expected, persisted even after careful statistical analysis. They hinted at primordial fluctuations or processes in the early universe not fully captured by models. While explanations like the integrated Sachs-Wolf effect or foreground contamination were proposed, some cold spots remain enigmatic, prompting questions about the uniformity of the early universe and the physics of inflation. All of these anomalies had one thing in common: they challenged expectations, yet most were eventually placed within a broader context. Tabby's star could be modeled with dust and debris. Oumuamua's acceleration could be explained by unconventional comet-like behavior. The Great Attractor and dark flow, while puzzling, mapped onto gravitational models at large scales. The cold spots continue to puzzle, but they are understood as fluctuations within a larger framework. Each anomaly offered clues, but none forced a complete rethink of what is possible in terms of motion beyond the observable universe. This is where the JWST object changes the game. Unlike Tabby's star, which flickered but stayed in place, or Oumuamua, which passed quickly through the solar system, this object moves outside the observable universe itself. It exists at a distance so extreme that its motion cannot be explained by nearby gravitational interactions. Its redshift indicates light that began traveling when the universe was in its infancy. Its trajectory is persistent and measurable, recorded directly in repeated JWST observations. This is unprecedented. Most anomalies were indirect or temporary. The Great Attractor was inferred through velocities, not direct light. Dark flow relied on statistical analysis across many clusters. Cold spots are temperature deviations, subtle and passive. The JWS object, by contrast, is detected directly as a moving point of infrared light, measurable across exposures. It is not inferred from motion of others or from fluctuations. It is tangible in JWST's field of view. The credibility of direct detection cannot be overstated. Previous anomalies always carried uncertainty about instruments or interpretations. Tabby's star dimming could be due to dust. Oumuamua might have been affected by unseen outgassing. Great Attractor calculations rely on modeling hidden mass. JWST's measurement of this object, its position, motion, and redshift, comes from a stable, calibrated, and highly sensitive instrument, orbiting far from Earth's interference. Each photon is a record, repeatedly confirmed across exposures, reducing the possibility of error. This object also pushes limits in terms of scale. Oumuamua was small, a single interstellar rock. Tabby's star was one star among billions. The Great Attractor affected clusters of galaxies. The JWST object exists beyond the edge of what can be observed at extreme redshift, suggesting it may not belong to any visible structure. Its apparent superluminal motion and isolation place it in a category entirely different from historical anomalies. It shows gaps in our knowledge about motion, large-scale structure, and the edge of the observable universe. Whereas past anomalies challenged details, why a star dimmed, why a cluster drifted, this object challenges the framework itself, revealing phenomena in a regime where LCDM has not been directly tested. It sits at the intersection of observation and theory, moving through a domain previously accessible only through prediction, not measurement. Unlike cold spots or dark flow, which are passive, this object is active. Its motion is measurable. Its infrared emission is detectable. It carries information across billions of years of cosmic history, providing a dynamic signal rather than a static anomaly. JWST doesn't just see that something is unusual, it watches it move. That motion is central because apparent trajectories at extreme redshift connect directly to cosmology, cosmic expansion, and the nature of spacetime itself. The object's persistence adds weight. One-off events like Oumuamua fade quickly, leaving only a brief trace. This object remains detectable across exposures, suggesting it is not transient but a stable structure with measurable properties. Its apparent motion, compact infrared signature, and distance make it a singular event, direct, verifiable, and ongoing. Historically, anomalies often sparked wild speculation. Tabby's star invited alien megastructures. Oumuamua triggered ideas about artificial probes. Dark flow fueled thoughts of physics beyond the standard model. This object, however, cannot be dismissed or explained away easily. Its direct detection, extreme motion, and unprecedented location force theorists to reconsider what is possible in terms of cosmic structures, flows, and unobservable regions. In terms of motion, scale, and observation method, the JWS detection stands alone. Tabby's star flickered, Oumuamua passed, the Great Attractor pulled invisibly. Cold spots varied passively. JWS's object moves across space in a way no previous anomaly has. Each frame, each repeated exposure, records subtle positional shifts, creating a measurable trajectory. It transforms the anomaly from speculation to something tangible, observable, and unprecedented. Potential explanations and hypotheses. The JWS object sparked a storm of discussion the moment its movement was confirmed. Scientists stared at the data, scanning each frame, analyzing each photon, trying to make sense of something that seemed impossible. At first, the simplest explanation often comes first. It could be a distant galaxy cluster, drifting along under the influence of gravity. Clusters of galaxies are not static. They interact, collide, and move along the cosmic web. They pull on each other, tugging stars, gas, and dark matter along with them. Could this object be part of such a massive structure, traveling in a path dictated by forces we only partially see. Clusters can accelerate under gravity, especially when multiple filaments intersect. The object might belong to an enormous, previously unseen cluster lying at the edge of what JWST can observe. Its apparent isolation could be deceptive. Light from neighboring galaxies may be too faint, too redshifted, or too obscured by dust to detect. The object could appear alone, moving mysteriously, when in reality it is simply tracing the path of a hidden mass. JWST's infrared imaging captures the object's photons, but even this incredible sensitivity has limits. There could be an entire web of faint galaxies accompanying it, invisible to current instruments, tugging it along with unseen gravitational hands. Next comes the possibility of data processing or instrumental artifacts. Every observation carries risk. Cosmic rays, detector noise, or subtle software glitches can produce strange signals. But this object has been observed across multiple exposures with careful calibration. JWST operates far from Earth at the L2 point, avoiding interference from atmospheric distortions or terrestrial light pollution. Each frame aligns with the previous. The movement persists across scans. The redshift matches expectations. If it were an artifact, it would likely appear random, inconsistent, or vanish with repeated observation. But this signal endures, coherent, measurable, and reproducible. Even the most meticulous teams double-checked algorithms. Automated software flagged subtle positional changes first, then human astronomers examined every detail. Cross-referencing with other telescopes was attempted. Hubble, though less sensitive in infrared, could provide partial confirmation. Ground-based arrays attempted to track correlated motion in nearby wavelengths. Every check reinforced the movement. Instrument error became increasingly unlikely. This object demanded serious consideration, not dismissal. Another conventional explanation involves unseen dark matter effects. Dark matter forms the backbone of the universe's structure, invisible yet dominant. It creates gravitational wells that guide galaxy formation, influence motions, and shape the cosmic web. Perhaps the object is moving under the influence of a dark matter concentration, undetectable by current instruments. This could be a hidden filament, a dense clump, or a flow channeling the object along a path that appears extraordinary from our vantage point. Dark matter cannot be seen directly, but its gravitational pull leaves measurable traces. JWST may have captured one of these traces in action. Some hypotheses combine multiple conventional effects. Imagine a distant galaxy cluster moving through a low-density region, guided by dark matter filaments, magnified by gravitational lensing. Its motion appears amplified because space itself is stretching at extreme redshift. Repeated exposures detect subtle shifts, giving the impression of extraordinary velocity. This scenario fits within known physics, yet produces motion that looks nearly impossible when viewed without context. Gravity alone could also accelerate objects at extreme redshift beyond what is typical nearby. Early universe regions were denser, richer in interactions. A cluster forming billions of years ago could have been influenced by massive structures just outside our current observable range. The object's path might trace these ancient gravitational currents. JWST captures the light traveling from these regions, revealing motion frozen into photons billions of years old. Still, none of these explanations fully account for the object's uniqueness. Clusters move, artifacts appear, dark matter influences trajectories, but the combination of extreme distance, persistent motion, and measurable redshift is unprecedented. Conventional hypotheses stretch to cover the observation, but each leaves lingering questions. That tension fuels deeper inquiry. Astronomers also consider the role of cosmic expansion in apparent motion. At extreme redshift, space stretches faster, magnifying small movements into what looks like superluminal displacement. A cluster moving gently could appear to drift across the sky at an extraordinary speed when measured from Earth. Infrared photons carry this history, tracing trajectories that are amplified by billions of years of expansion. JWST can detect these amplified movements, revealing motion invisible to previous telescopes. Dark matter effects are more subtle. Invisible structures can accelerate objects, creating paths that defy local intuition. These flows are part of the cosmic web, massive and sprawling. The object's trajectory may align with a hidden filament or a flow extending beyond the observable universe. This could explain both its apparent isolation and unusual velocity, though proving it requires correlating motion with unseen mass, a challenge at extreme redshift. Instrumental artifacts remain a minor possibility, though each layer of verification reduces their likelihood. Repeated exposures, cross-checking with different detectors, and careful calibration all support the object's reality. If this were a glitch, it would appear inconsistent, vanish under different conditions, or fail to replicate across frames. Yet, the motion persists, coherent and measurable, confirming that something real exists, something that has traveled billions of years across expanding space. Even combining all conventional explanations, cluster motion, dark matter influence, cosmic expansion, lensing, the object remains unusual. It occupies a parameter space at the edge of detectability in a regime where few direct measurements have existed. JWST provides the first direct glimpse of motion at this scale, revealing not just presence, but trajectory, speed, and redshift. This combination of properties challenges expectations, even if it can still be framed within known physics. The object's infrared signature adds weight to conventional explanations. Brightness and spectral features suggest either a dense collection of stars, hot gas, or dust. Each could exist within a moving cluster, accelerated by gravity and dark matter. Yet the object remains compact and isolated in observations, implying that conventional cluster models would need to be stretched to account for its trajectory. Its apparent coherence over time makes it unlike diffuse gas clouds or tidal debris, hinting at something more substantial. A bound structure moving persistently across the sky. Even data processing hypotheses cannot fully mimic redshifted motion. Instrumental glitches rarely reproduce both movement and spectral properties simultaneously. JWST captures light across multiple infrared bands, revealing energy distribution consistent with extremely distant sources. Artifacts cannot generate redshifted spectra corresponding to billions of years of travel, while also moving in a coherent trajectory. Every measurement reinforces that the object is not a fluke, not a cosmic mirage, but a real entity with properties demanding explanation. Gravity, dark matter, cosmic expansion, and instrumental checks form the starting point. Each provides plausible mechanisms for motion, yet the object sits at an intersection that remains unprecedented. It's distant, moving, infrared bright, and coherent. Conventional physics can stretch to accommodate aspects of its behavior, but it resists simple categorization. The more astronomers examine it, the more it tests assumptions about how structures behave at extreme redshift. Even if this object turns out to be a distant cluster, moving along a hidden filament, guided by dark matter and amplified by cosmic expansion, it still represents a phenomenon never observed directly before. Previous anomalies were often inferred indirectly. This is a moving point of light, measurable, reproducible, and persistent, captured with a telescope capable of seeing farther and more precisely than any before. It transforms speculation into concrete observation, forcing conventional hypotheses to stretch to the edge of plausibility. This is where JWST's sensitivity matters. Detecting faint infrared photons from the earliest universe allows astronomers to see motion at extreme redshift, a domain inaccessible before. Every shift across the detector is encoded with billions of years of history. Conventional explanations, gravity, clusters, dark matter, interact with redshift, expansion, and observational sensitivity to produce a signal that looks almost impossible from Earth. Yet it is grounded in real, measurable phenomena, waiting to be unraveled. Exotic physics. The JWST object does more than challenge conventional explanations. Its behavior nudges astronomers toward realms of physics rarely explored in direct observation. Extreme distance, extreme motion, and persistence across multiple exposures hint at processes stretching back to the universe's earliest moments, to a time when the rules were far less familiar. Some of the first possibilities involve relics from the early universe. Inflation, the rapid expansion that occurred fractions of a second after the Big Bang, could leave structures frozen into the cosmic fabric. Most of these primordial imprints are subtle, detectable only in the microwave background or in large-scale clustering. But a relic massive enough, compact enough, and radiating in infrared could survive across billions of years, moving along trajectories imprinted during those first moments. The JWST object might carry the signature of that era, a survivor from a time when space itself stretched faster than the speed of light. These relics could be dense clumps of matter formed before normal galaxy formation. Some might contain early stars or proto-galaxies, tiny pockets of energy and matter left over from inflation's turbulence. As the universe expanded, these pockets would drift, isolated from the cosmic web forming around them. They could appear to move independently, their motion influenced by ancient gravitational forces, amplified by space expansion over billions of years. JWST's infrared eyes capture the faint glow, tracing motion that encodes the early universe's dynamics in ways no telescope before could observe. The object also hints at multiverse interactions. If our universe is one bubble in a larger cosmic foam, collisions with neighboring bubbles could leave subtle marks. A structure propelled or shaped by such a collision might appear outside typical cosmic flows. Its apparent velocity, direction, and isolation could reflect forces acting beyond our observable bubble. These interactions would be rare, leaving few survivors. JWST may have caught one. A collision billions of years ago could have ejected matter into the periphery of our universe, producing an object whose motion seems alien compared to standard cosmological expansion. Even more extreme, this could be a high-energy phenomenon. Supermassive black hole jets, primordial quasars, or hypermassive energy streams might produce compact, moving infrared sources detectable at extreme redshift. Black holes formed in the first billion years could launch jets with extraordinary energy, influencing surrounding matter and radiation. If the JWST object is the infrared signature of such a jet, its apparent motion could represent the propagation of energy along vast cosmic distances. Early quasars could account for the brightness and coherence across repeated exposures, while extreme redshift stretches light into JWST's infrared sensitivity. Primordial quasars themselves are fascinating. They formed before ordinary galaxies fully assembled, containing immense energy and mass in compact cores. Motion from gravitational interactions or ejection from dense early structures could create trajectories appearing independent of cosmic filaments. Over billions of years, cosmic expansion magnifies tiny intrinsic movement into apparent rapid displacement. JWST may be observing one of these rare, early cosmic engines in action, its photons traveling from the universe's infancy to reveal motion unimaginable from nearby scales. Exotic physics also opens the possibility of unknown high-energy processes. Jets or streams from massive objects could move matter in ways conventional models underestimate. Interaction with dark energy, early universe magnetic fields, or extreme density gradients might produce trajectories and infrared signatures unlike any nearby phenomenon. The JWST object could be a natural laboratory, showing physics operating at energy scales and distances inaccessible by any other means. Some models suggest that ancient energy relics could persist in isolated regions. Compact clusters of hot gas, radiation, or protostructure could drift through low-density space, unaffected by standard filaments. Their motion, combined with gravitational lensing and cosmic expansion, could produce apparent velocities that challenge conventional understanding. JWST's repeated scans capture subtle angular shifts in such relics, making their ancient motion measurable for the first time. Another possibility lies in primordial black holes. These hypothetical objects, formed before ordinary star formation, could generate infrared emission through accretion or surrounding gas. Moving independently through early cosmic voids, they would appear isolated and could trace extreme trajectories, influenced by ancient gravitational forces and local expansion. Detection would reveal matter surviving from the universe's earliest epochs, moving along paths encoded in primordial conditions. Exotic physics also considers energy propagation across extreme distances. High-energy streams from early universe phenomena could appear as compact points of infrared light if the emission is collimated or concentrated. Their motion, when stretched by cosmic expansion, could mimic independent movement across billions of light-years. JWST's ability to track these shifts transforms previously theoretical high-energy phenomena into observable events. Interactions between relic structures and the cosmic web could amplify motion. Even sparse dark matter filaments could channel movement in ways conventional models do not predict. A relic object moving along a hidden filament might appear isolated while tracing a path set billions of years ago. Infrared detection captures photons that encode both position and energy, revealing a moving relic interacting with unseen forces. Some exotic hypotheses even entertain the possibility of structures ejected from other universes or regions beyond our bubble. A collision in a neighboring bubble or a fragment of space carrying coherent matter and energy could enter our observable universe, producing an infrared source with measurable motion. Its apparent trajectory could be unprecedented because it originates outside standard cosmic scaffolding. JWST may have glimpsed matter shaped by physics beyond our universe, moving across distances and redshifts that encode its extraordinary origin. High-energy astrophysics also offers explanations for persistent motion. A jet from a supermassive black hole or an early quasar could generate a compact infrared hotspot. As the jet interacts with surrounding gas or dust, it may appear to shift across space when observed over repeated exposures. Extreme redshift stretches and amplifies motion, creating trajectories that seem to exceed ordinary limits. JWST's observations capture both energy and movement, providing direct evidence for phenomena otherwise invisible. Even more speculative, this object could represent a combination of relic formation and exotic energy processes. A dense primordial clump, ejected or shaped by early universe turbulence, interacting with high-energy jets or magnetic fields, could produce measurable motion across infrared wavelengths. Its trajectory would not fit conventional flows, but remain consistent with physics operating at extreme energy and distance scales. JWST's sensitivity allows it to detect this combination, producing an observable anomaly at the frontier of known cosmology. Finally, exotic physics forces consideration of unknown mechanisms. The universe at extreme redshift, in regions near the edge of observability, may host processes entirely absent nearby. These could involve interactions between dark energy, inflationary relics, or previously unseen particle physics phenomena. The JWST object might carry traces of such physics in its motion, redshift, and infrared emission. Its trajectory becomes a direct record of forces operating where standard measurements have never reached. JWST transforms these exotic possibilities from theory into observation. Each repeated exposure records photons traveling billions of years, revealing motion, energy, and distance. The object may be a relic, a jet, a primordial quasar, or a fragment from outside our universe. It might combine several exotic processes. Its infrared signature, persistence, and motion provide direct data where previously only speculation existed. Every hypothesis emphasizes the extraordinary. Extreme redshift stretches light into infrared. Cosmic expansion amplifies small intrinsic motion. Gravitational lensing or hidden filaments shape trajectories. Early universe relics, jets, quasars, or multiverse fragments leave traces that persist across billions of years. JWST captures these traces, revealing a moving object that sits squarely at the edge of what is known, what is predicted, and what has been imagined in theoretical physics. How JWST captured it, the science of detection. JWST's detection of the moving object at the edge of the observable universe didn't happen by chance. It was a combination of extraordinary instruments, precise techniques, and relentless scrutiny. The story begins with the telescope itself, perched nearly 1 million miles from Earth, at the L2 point, far from Earth's heat, vibrations, and atmosphere. Floating in deep space, JWST has a stable platform that allows it to stare at one patch of sky for hours, days, and sometimes weeks, without interruptions that plague ground-based observatories. The first instrument that captured the initial light of the object is NIRCam, the near-infrared camera. NIRCam is the telescope's workhorse for imaging the distant universe. Its detectors are exquisitely sensitive to infrared light, the kind emitted by ancient galaxies whose visible light has been stretched over billions of years by cosmic expansion. This sensitivity allows JWST to see through cosmic dust, to penetrate regions that Hubble or ground-based telescopes cannot, and to capture light from objects that formed when the universe was just a fraction of its current age. NIRCam's wide field and high resolution make it ideal for deep surveys, revealing countless faint sources in a single exposure. But NIRCam alone isn't enough. Once the object was detected in images, NIRSpec, the near-infrared spectrograph, provided the next layer of insight. NIRSpec spreads incoming light into its component wavelengths, producing spectra that encode the object's distance, composition, and motion. Redshift measurements from NIRSpec revealed that the object is at extreme distances, corresponding to light that has traveled for over 13 billion years. Its spectrum showed subtle signatures hinting at stellar populations, gas or dust, allowing astronomers to distinguish a moving galaxy, cluster, or exotic high-energy phenomenon from background noise. MIRI, the mid-infrared instrument, complements NIRCam and NIRSpec. Sensitive to longer infrared wavelengths, MIRI captures even cooler or dust-obscured sources, providing a more complete picture of the object's energy output. For an object this distant, MIRI's detections confirm that the infrared emission is real and persistent, not a transient flare or instrumental anomaly. Together, NIRCam, NIRSpec, and MIRI form a trio capable of capturing light from the very edge of the observable universe, each adding a layer of confirmation and precision. Detection isn't just about pointing the telescope and taking pictures. Astronomers employ time series imaging, repeatedly scanning the same field over days, weeks, or months. Each exposure captures a snapshot of the universe frozen in time. Subtle shifts between images reveal motion. For an object billions of light years away, these shifts are tiny, measured in milliseconds. Detecting them requires meticulous alignment, calibration, and removal of background noise. Automated software flags potential movers, but human eyes and expertise remain critical in verifying that the signal is genuine. Long exposure imaging is another essential technique. Objects this distant are faint, often emitting just a handful of photons per second in the infrared. JWST can integrate light over hours, accumulating enough photons to produce a clear detection. The longer the exposure, the fainter the sources that emerge from the background. But long exposures introduce challenges. Cosmic rays can strike the detector, stray light can contaminate the signal, and slight thermal variations can produce noise. Sophisticated data processing removes these effects, leaving only the true light from the object. Tracking motion at such extreme distances presents a unique challenge. Apparent shifts are minuscule, and redshift stretches the light, reducing apparent brightness. The telescope must maintain stable pointing, avoiding drift over the course of multiple exposures. Even tiny vibrations from the spacecraft or temperature fluctuations in its instruments can blur the image, hiding the object's motion. Engineers designed JWST to minimize these effects, using gyroscopes, reaction wheels, and active control systems to keep the telescope steady, enabling detection of motion otherwise impossible to observe. The infrared spectrum is critical in this process. Light from the early universe arrives stretched into the infrared. Visible light telescopes would see almost nothing. Infrared allows JWST to detect not just the presence of the object, but its movement. Subtle differences in infrared intensity across repeated exposures reveal shifts in position. The combination of redshift measurement and angular motion allows astronomers to calculate a trajectory, even at the extreme edge of space and time. Confirming a moving source requires cross-checks and verification. Astronomers examine each frame, comparing against previous observations. They look for patterns in the background stars and galaxies to rule out misalignment or spurious effects. They consult multiple instruments, NIRCam, NIRSPEC, MIRI, to ensure the motion isn't limited to a single detector. They check for cosmic rays, electronic interference, and transient phenomena that could mimic motion. Only when all independent lines of evidence point to the same movement can the object be considered real. Behind the scenes, teams of scientists work in shifts, reviewing terabytes of data. Automated pipelines highlight potential movers, but expert eyes confirm subtle shifts, measure redshifts, and model motion relative to cosmic expansion. Each photon is treated as a message from billions of years ago, carrying information about position, motion, and energy. Cross-referencing with catalogues of known galaxies ensures the object isn't a foreground source. Observations are repeated, exposures extended, and the object's trajectory carefully plotted against background stars and cosmic filaments. Infrared detection at these distances also reveals intrinsic properties. The object's brightness, spectrum, and motion allow astronomers to distinguish between a cluster of galaxies, a massive quasar, or a compact relic of the early universe. NIRSPEC spectra reveal emission lines that hint at the presence of hydrogen, helium, or dust, while MIRI shows longer wavelength emissions consistent with thermal processes or heated gas. This multi-wavelength approach ensures the detection is robust and the motion is measurable, not an artifact of a single instrument. JWST's stability is another key factor. At L2, it avoids the wobble, vibration, and atmospheric distortion that plague Earth-bound telescopes. It can stare at the same field for tens of hours, enabling continuous exposure without interruption. This stability allows detection of movement that would be imperceptible in ground-based observations, or even with Hubble. Each exposure builds a time-lapse of the universe's motion, capturing something truly extraordinary, a moving object at the edge of space itself. Finally, confirming a moving source at this extreme distance involves repetition and peer review. Data is analyzed multiple times by different teams using independent methods. Slight shifts in position are measured against background stars and distant galaxies. Redshift and brightness are cross-checked across instruments. When all these independent observations converge, the object is confirmed not just as a point of light, but as a moving entity, a cosmic traveler whose journey spans billions of years. Implications for cosmology and physics. The JWS detection does more than reveal a single moving object at the edge of the observable universe. It reaches deep into the very fabric of cosmology, shining light on mysteries that have haunted astronomers for decades. The Standard Model of Cosmology, LCDM, lambda cold dark matter, has been remarkably successful at explaining large-scale structure, galaxy formation, and cosmic expansion. It predicts how matter clumps, how galaxies move, and how light stretches as the universe grows. Yet, this moving object challenges assumptions built into that model. Its extreme redshift places it at a distance where cosmic expansion dominates local motion. Observed velocities appear extraordinary, hinting at dynamics that standard LCDM might not fully capture. Could there be forces at work we haven't accounted for? Hidden filaments of dark matter? Subtle interactions between early universe structures? Or even something more exotic, operating at the edge of our observable bubble? The detection forces a confrontation with the unknown, showing that there may be motion, structures, or forces beyond what current models predict. Beyond gravity and dark matter, this object could hint at previously unseen dimensions or hidden physics. Some theories propose that our universe might interact with others or contain dimensions imperceptible to ordinary matter. A moving structure at extreme redshift, persistent and isolated, could be a rare glimpse into these realms. Its trajectory, speed, and infrared signature may carry information about forces or geometry outside conventional observation, encoded in photons traveling for billions of years. Future telescopes will play a decisive role. The Nancy Grace Roman Space Telescope, with its wide field of view and deep infrared sensitivity, could capture complementary surveys, scanning large patches of sky to locate similar moving objects. The Extremely Large Telescope, ELT, on Earth, with its unprecedented resolution, could follow up on the spectrum, composition, and motion of these objects, providing higher fidelity redshift measurements and probing smaller-scale structure. Next-generation radio arrays could detect synchrotron emissions or interactions with cosmic magnetic fields, offering a multi-wavelength view that confirms or challenges JWST's infrared detection. Each of these instruments extends our reach further. JWST opened the door, revealing a moving object at the edge of observability. Roman, ELT, and future radio arrays could map a population of such objects, turning a singular detection into a dataset of extreme cosmological phenomena. Patterns might emerge, clusters of moving relics, aligned trajectories along hidden filaments, or energy flows tracing early universe conditions. These follow-ups would provide the context needed to understand whether this object is a rare anomaly or the first glimpse of a widespread, hidden cosmic behavior. The implications for cosmic expansion are profound. The object's apparent motion challenges simple interpretations of Hubble flow. At extreme redshift, expansion stretches distances and light, and even small intrinsic motion can appear amplified. But this object's trajectory seems coherent, measurable, and persistent, suggesting that there could be local deviations or flows in early universe expansion unaccounted for in current models. Tracking such deviations could refine our understanding of dark energy, the mysterious force accelerating expansion, revealing how it influences motion on scales far beyond galaxies and clusters. The universe's topology might also come into focus. If hidden structures or exotic physics guide motion at extreme redshift, this could provide evidence that space itself is more complex than a simple expanding sphere. Filaments, voids, or even bubble-like structures might influence trajectories in subtle ways, producing apparent motion that defies expectations. JWST may have captured one such signature, a moving point of light carrying encoded information about the universe's shape, connectivity, or hidden pathways along which matter and energy travel. This discovery forces cosmology to expand its boundaries. Until now, most observations tested models within the observable universe, regions where predictions aligned closely with data. A moving object at extreme redshift operates at the edge of what we can observe, where photons arrive from regions rarely probed directly. These photons carry not just position and brightness, but encoded history of gravitational interactions, energy flows, and possibly exotic physics. They serve as messengers from the very limits of reality, hinting at processes that could rewrite models of structure formation, cosmic evolution, and even fundamental laws. Dark energy may be involved in unexpected ways. Its influence dominates cosmic expansion, shaping large-scale motion. This object's trajectory could trace how dark energy acts on isolated structures at extreme distances. If future observations reveal similar moving objects, patterns may emerge, showing that dark energy interacts with matter in ways currently invisible in nearby galaxies or clusters. Infrared measurements, repeated over months or years, will refine models, helping astronomers determine whether the object's motion is amplified by expansion, shaped by hidden structure, or driven by new physics. The universe might be hiding a dynamic dance of motion beyond what we can see. JWST captures a single point in that dance, but its significance lies in what it reveals about hidden activity at cosmic edges. This moving object may be the first tangible evidence that the cosmos is not static at the largest scales. There may be streams of matter, relic structures, or exotic phenomena quietly moving, guided by forces or geometry beyond our current reach. Each exposure from JWST acts as a frame in this cosmic movie, showing motion previously invisible. teasing patterns that could reshape our understanding. Imagine the possibilities. A population of moving early universe relics, each tracing paths through hidden filaments. Jets from primordial quasars pushing matter across vast distances. Structures shaped by interactions beyond our observable bubble. Every photon encodes not just light, but the history of forces acting billions of years ago. These moving points could provide a new tool for cosmology, a way to map expansion, dark energy, and topology with direct motion, not just static light. Future observations will test theories rigorously. Infrared surveys, deep spectroscopy, and multi-wavelength tracking can determine if this is a singular phenomenon or part of a broader class of cosmic movers. ELT and Roman can provide high-resolution follow-up, measuring the object's spectrum in detail, tracing elemental abundances, star formation rates, or gas content. Next-generation radio arrays could detect synchrotron or plasma emission, revealing energetic interactions unseen in infrared alone. Together, these instruments will transform a single JWST detection into a multifaceted dataset, unlocking insights into physics at extreme scales. Each discovery like this challenges assumptions. Cosmologists may need to refine models of motion at extreme redshift, adjust simulations of structure formation, and consider how dark energy operates across isolated regions. The object provides direct evidence of phenomena that were previously theoretical, offering a testing ground for hypotheses ranging from hidden dark matter flows to multiverse interactions. Its persistence, motion, and infrared signature are a call to re-examine what is possible in the universe's outermost reaches. The moving object also redefines the concept of distance and motion. Photons arriving from billions of light-years away are stretched, time-dilated, and influenced by expansion. JWST allows astronomers to translate these subtle shifts into measurable trajectories, revealing how ancient structures traveled through expanding space. This makes the edge of the observable universe a laboratory, a place where motion, energy, and structure intersect, visible only through sensitive infrared detection. The implications extend to fundamental physics. If unknown forces or hidden dimensions influence motion at these distances, JWST provides the first observational clue. Future telescopes could trace patterns, determine the nature of these forces, and test whether physics at extreme redshift differs from local conditions. The universe might contain mechanisms guiding matter and energy in ways invisible in nearby galaxies, revealing hidden structure, flows, or interactions. Each follow-up observation builds on JWST's initial capture. Time series imaging over months or years allows measurement of acceleration, trajectory curvature, and changes in brightness. These data provide input for simulations, testing whether conventional gravity, dark matter, or cosmic expansion suffice to explain motion, or whether new physics is required. Repeated detection also confirms persistence, ensuring that transient phenomena do not mimic extreme motion behavior. In practical terms, this discovery may reshape observational strategy. Astronomers could begin scanning for moving objects systematically, looking for trajectories at extreme redshift rather than just static sources. JWST has proven it can detect movement where no telescope could before. Future surveys might reveal entire populations of moving structures, allowing cosmologists to map motion as a direct tracer of hidden forces, energy flows, or early universe dynamics. This detection demonstrates the power of multi-instrument synergy. NIRCam locates faint sources, NeoSpec measures spectra, MIRI confirms energy distribution, and repeated exposures track motion. Each photon contributes to a detailed picture of motion, distance, and energy at cosmic edges. JWST acts not just as a camera, but as a time machine and motion detector, capable of revealing dynamics across billions of years. The object may also provide clues about the shape and connectivity of the universe. Trajectories at extreme redshift may trace hidden filaments, isolated relics, or energy flows shaped by topology. Measuring motion along these paths could reveal connections between regions previously thought independent. JWST gives the first window into these patterns, hinting at a universe far more intricate and dynamic than imagined. Ultimately, the moving object shows that the universe is not static, not uniform, and not fully understood. Even at the edge of observability, motion persists, structures travel, energy flows, and hidden forces guide them. JWST allows direct detection of these phenomena, turning theory into observation. It transforms the invisible into the measurable, offering a glimpse of the hidden dance of motion at the outermost reaches of reality. Future observations and the race to understand. The detection of a moving object at the edge of the observable universe is not the end. It is the beginning of a global effort, a race to understand something that may redefine how we perceive the cosmos. JWST captured the first glimpse, but scientists know that a single observation is only the start. Follow-up plans are already underway, orchestrated across multiple continents, observatories, and instruments. Every photon counts, every exposure matters, and the coordination is unprecedented. JWST itself will revisit the field, focusing longer, deeper, and with greater spectral precision. Time series imaging campaigns are being planned, where the telescope will return to the same patch of sky repeatedly, building a continuous record of motion. These exposures will stretch over weeks and months, capturing subtle shifts in position. The goal is not just to confirm motion, but to measure acceleration, to see if the object's trajectory curves or twists, and to detect interactions with the surrounding cosmic environment. Infrared spectra will be refined, emission lines mapped with precision, and faint structures surrounding the object will be examined to determine whether it is a solitary traveler or part of a larger system. Astronomers worldwide are coordinating to maximize coverage. Ground-based observatories with adaptive optics, like the Extremely Large Telescope, will complement JWST's infrared observations. Teams in North America, Europe, and Asia are aligning schedules to capture simultaneous observations, ensuring no detail is missed. Every image, every spectrum is cross-referenced across instruments to rule out artifacts, verify motion, and track subtle changes. This collaborative approach transforms a single discovery into a global campaign, merging the sensitivity of space telescopes with the resolution of terrestrial giants. Supercomputers are becoming central to understanding what JWST sees. Simulations of extreme redshift objects, cosmic expansion, and gravitational interactions are run on the largest computing clusters. These models test motion scenarios, exploring how relic structures, early universe jets, or isolated clusters might travel across billions of light years. By inputting JWST data, redshift, trajectory, spectrum, researchers can compare predicted paths to the observed motion, refining hypotheses and narrowing possibilities. Each simulation produces thousands of virtual universes, each with slightly different physics, to see which conditions could reproduce the observed behavior. The modeling effort also includes gravitational lensing. Massive structures between us and the object could bend light, producing apparent motion or magnifying faint signals. Supercomputers calculate countless lensing scenarios, tracing how photons traverse warped space-time, separating lensing effects from intrinsic motion. These calculations require extreme precision, because even tiny deviations could lead to false interpretations. Only by integrating data, simulations, and repeated JWST observations can astronomers confidently determine whether the motion is real, apparent, or a combination of both. Looking beyond JWST, speculative missions are already on the drawing board. Deep infrared observatories could sweep wider regions of sky, searching for similar moving objects, mapping a population of distant relics. X-ray telescopes may detect high-energy emissions, revealing supermassive black holes or energetic jets invisible in infrared alone. Gravitational wave observatories, sensitive to the ripples from massive cosmic events, could potentially detect interactions or collisions involving these moving structures. Each wavelength, each method, contributes a new dimension to the puzzle, ensuring that no aspect of the phenomenon remains hidden. The international effort is unprecedented, not only in scope, but in ambition. Astronomers are designing campaigns where JWST, ELT, Roman, and future missions observe in tandem. Simultaneous data from multiple wavelengths allow cross-validation, reducing uncertainty and increasing confidence in motion measurements. Teams are developing pipelines to process massive data sets in near real time, flagging subtle changes that might otherwise go unnoticed. Algorithms scan terabytes of images, highlighting shifts as small as a millisecond. Then human experts verify and interpret them. Time is a critical factor. Motion at extreme redshift unfolds slowly from our perspective, but missing exposures could mean losing vital clues. The cadence of observations, how frequently telescopes return to the same patch of sky, is being optimized to capture every stage of motion. Long exposures allow detection of faint emission, while frequent revisits ensure movement is not overlooked. Each campaign is a delicate balance between depth, frequency, and coverage, requiring careful planning and coordination across the globe. Simulations also explore exotic physics scenarios. If the object represents a relic from the early universe, models test how inflationary turbulence, primordial black holes, or early jets could produce the observed motion. If the object originates from interactions beyond our observable bubble, multiverse collision models are run, tracing how matter could traverse unknown physics while leaving detectable traces. High-energy phenomena are simulated as well, testing how jets, magnetic fields, or dark matter structures could create trajectories matching JWST data. These virtual experiments guide observation, helping astronomers decide where to point telescopes next. The race to understand is not limited to professional astronomers. Citizen science projects are being organized to crowdsource analysis. Volunteers examine sequences of images, searching for subtle motion patterns, anomalies, or transient features. These efforts increase detection sensitivity, providing independent verification of automated algorithms, and potentially revealing additional moving objects that were missed in initial scans. Every eye on the sky contributes to the global understanding of this mysterious traveler. Planned JWST follow-ups will also include spectroscopy at higher resolution. By measuring fine details in emission lines, astronomers can infer velocity dispersion, chemical composition, and gas dynamics. This data is crucial to distinguish between conventional galaxies, clusters, or exotic early universe phenomena. Variations in brightness combined with spectral information may reveal interaction with surrounding structures, unseen filaments, or energy flows influencing motion. Future missions could expand the search even further. Deep infrared observatories with larger fields of view would enable surveys of entire sky regions, detecting rare movers that JWST's narrow focus might miss. X-ray observatories could detect energetic emissions from primordial black holes, quasars, or jets, providing independent confirmation. Gravitational wave arrays could detect subtle disturbances caused by massive objects moving or colliding at extreme distances, offering an entirely new channel for observation. Together, these missions could build a multi-messenger view of the outermost universe. The race is not just to observe, but to understand implications. Every follow-up observation feeds simulations, which in turn guide new campaigns. Patterns in motion, distribution, and spectral properties might reveal hidden cosmic filaments, relic structures, or unknown forces. Detecting a second, third, or fourth moving object could transform a singular anomaly into a population, allowing statistical analysis and more robust conclusions. The coordination is global and relentless. Teams share data in near real time, combining infrared images, spectra, and simulations. Algorithms are trained on JWST observations, then applied to other datasets, looking for similar anomalies. Networks of telescopes are synchronized, from space-based observatories to ground-based giants, maximizing coverage across multiple wavelengths. Every exposure, every photon, becomes part of a collective effort to map motion at the edge of the observable universe. Astronomers are also experimenting with predictive modeling. Based on current motion, they can forecast where the object will appear in future exposures. This allows telescopes to pre-allocate observation time efficiently, ensuring no motion is missed. Combined with multi-wavelength detection, these predictive models optimize global coordination, increasing the chance of capturing rare phenomena as they unfold. Speculative missions could push beyond traditional observation. Ultra-deep infrared observatories might detect fainter, more distant moving structures. Next-generation X-ray and radio arrays could probe energy flows and plasma interactions across billions of light-years. Gravitational wave detectors could sense the mass movements of relic structures, providing data entirely independent from light. Each method expands the scope of observation, increasing the likelihood of understanding the physics behind this extraordinary motion. Simulations continue to play a vital role. By creating virtual universes with extreme redshift objects, high-energy phenomena, or multiverse interactions, astronomers test which scenarios reproduce the observed motion. Results feed back into observational strategy, highlighting which regions of sky or wavelengths are most promising. These computational experiments bridge theory and observation, guiding the global campaign and maximizing the scientific return. As follow-ups progress, astronomers remain alert for surprises. The object might change brightness, reveal surrounding structures, or exhibit unexpected acceleration. Each new observation provides additional constraints, narrowing hypotheses and refining models. Patterns in motion could emerge, hinting at cosmic flows, relic populations, or previously hidden physics. JWST opened the first window, and the global network of instruments will continue to expand that view frame by frame, year by year. The race is as much about precision as speed. Extreme redshift objects require meticulous calibration, careful data reduction, and repeated verification. Small errors could mimic motion or hide genuine shifts. Teams around the world work in parallel, independently confirming results, ensuring that every detection is robust and every measurement trustworthy. Only with this precision can cosmologists hope to decode the information carried by photons traveling from the universe's edge. Each exposure is treated like a time capsule. Light that traveled billions of years contains not just information about location and motion, but about energy, composition, and the conditions of the early universe. JWST, combined with future missions, allows astronomers to read this message, revealing motion patterns that were previously theoretical. Every pixel, every spectral line, is part of a story written across cosmic time. The race to understand this object is a race for knowledge at the frontier of science. It combines space-based infrared observations, ground-based spectroscopy, simulations, multi-wavelength follow-ups, and global coordination. It is a race to capture motion at the limits of detectability, to interpret phenomena billions of years old, and to uncover physics operating in extreme conditions. Astronomers are already imagining the possibilities. If more moving objects are discovered, a hidden population could be revealed, tracing paths through cosmic voids, along filaments, or beyond the observable bubble. Patterns of motion could indicate new forces, unknown structures, or dynamics from the early universe. The combination of observation, simulation, and theory may produce the first direct mapping of motion at the edge of reality, a phenomenon previously confined to equations and speculation. Every follow-up campaign adds resolution, depth, and context. JWST revisits, Roman surveys, ELT spectroscopy, and radio or X-ray arrays together produce a multi-dimensional view. Algorithms track motion across exposures, simulations recreate dynamics, and cross-validation ensures reliability. The moving object becomes more than a point of light. It becomes a tracer of hidden physics, a window into the universe's most extreme conditions. The race to understand is ongoing. It involves planning years of observations, analyzing terabytes of data, and refining models based on every new photon. It requires international collaboration, combining the capabilities of multiple telescopes, instruments, and computational centers. It stretches human ingenuity to detect, measure, and interpret motion at the cosmic frontier. The object discovered by JWST may be unique, or it may be the first of many. Future observations could reveal a pattern, a population, or even entire streams of moving matter at extreme redshift. Each discovery expands our understanding of cosmic structure, early universe processes, and potentially exotic physics. This global campaign combines observation, simulation, and collaboration, extending humanity's reach to the very edge of the observable universe. Every exposure, every spectrum, and every simulated trajectory contributes to a deeper understanding of motion, energy, and structure at cosmic extremes. JWST has opened the door, and the worldwide network of telescopes and supercomputers is rushing to explore what lies beyond, frame by frame, photon by photon across billions of light years.